In the core of a star, everything is still, not the stillness of empty space, where nothing moves because nothing is there. A different kind of stillness entirely. The stillness of two enormous forces pressing against each other with perfect and equal weight, the way two hands pressed flat against each other from opposite sides hold a sheet of paper motionless between them. On one side, gravity, the accumulated pull of a mass so large that every particle within it is drawn toward every other particle with a force that summed across the whole amounts to a pressure no ordinary material could survive. On the other side, light itself, pouring outward from the nuclear fires at the center, pushing against the weight of all that matter above. Between those two forces, the star simply holds. It holds for a very long time. The time scale is difficult to approach directly. 8 billion years, 10 billion years. Numbers that long have no honest emotional equivalent, no comparison the body can fully inhabit. So approach it sideways instead. A single human life, generously measured, is something less than a century. 100 human lives laid end to end reaches back before the birth of writing. 1,000 lives takes the count to before agriculture. 1,000,000 lives reaches back past the appearance of our species. And still that is only 100,000 years, not even the blink, not even the first fraction of a fraction of the time a sun-like star spends simply burning. In the time a star like the sun holds itself in that quiet equilibrium between light and gravity, everything that has ever been human and everything that ever will be fits inside a margin too thin to measure against its length. The fire at the center is steady. Protons, the bare nuclei of hydrogen atoms, stripped of their electrons by the temperature, colliding at speeds the mind struggles to hold, are driven close enough together by the pressure and heat of the core that they fuse. 2 protons merge, then a third nucleus joins, then a fourth. The chain of collisions follows a path that ends, each time with the production of a helium nucleus. 4 protons have become one, slightly lighter nucleus, and the small difference in mass has become energy. Pure energy, released as a gamma ray, a photon of light so energetic it carries more punch than visible light by orders of magnitude. That photon does not travel far. Within the dense plasma of the stellar interior, a gamma-ray photon survives for an extraordinarily short time before it collides with another particle and is absorbed. It is re-emitted. It travels a tiny distance and is absorbed again. Each absorption and re-emission sends it off in a random direction so that its net progress outward through the star is not a straight path, but something more like the wandering of a grain of pollen in water, knocked one way, then another, then back toward the center, then sideways, then outward again by chance. This random walk through the stellar interior takes time. The estimate runs to roughly 100,000 years, which is to say, the energy released in the core of a star today will not reach the surface for 100,000 years. The light that leaves the sun on any given morning is not the fresh product of today's fusion. It is old energy, energy that has been making its slow, interrupted way outward since before our species existed in anything like its present form. When it finally reaches the surface, it is no longer a gamma ray. It has been absorbed and re-emitted so many times, its energy spread across so many photons, that it emerges as ordinary visible light, yellow-orange, spreading outward across space at the speed light travels, covering the distance between the sun and the earth in just over 8 minutes. It had been traveling for 100,000 years and crossed the final distance in 8 minutes, the vast middle of the journey, was all interior, all slow, all dark. The star does not hurry. It does not need to. The hydrogen in the core is enormous in quantity, and the rate at which it burns is set by the same equilibrium that gives the star its stillness, a careful balance between the need to generate enough pressure to hold the star up and the need not to generate so much that the star blows itself apart. The balance is self-correcting. If the core burns a little hotter and produces more pressure, the star expands slightly, and the expansion cools the core, slowing the burning. If the core cools a little and gravity begins to win, the core contracts, and the contraction heats it, restoring the burn rate. The star breathes in this sense very slowly over millions of years, making tiny adjustments, but across geological time, it is stable. It is patient in a way that has no human analog. Somewhere in the core, across all of those billions of years, the helium builds. Every fusion reaction that converts hydrogen to helium leaves behind a helium nucleus, where a hydrogen nucleus was before. The core is a place where hydrogen is consumed and helium accumulates, and unlike hydrogen, helium at these temperatures and pressures does not fuse. It simply sits. It accumulates. Over billions of years, the proportion of hydrogen in the core falls, and the proportion of helium rises, and eventually the core reaches a point where there is no longer enough hydrogen left to sustain the fusion reactions that have been holding the star up all this time. The fire at the center does not go out all at once. The hydrogen in the core is exhausted first, but hydrogen still burns in a shell surrounding the now inert helium core, and that shell burning releases energy at a different rate, driving changes in the star's structure that are slow by human reckoning, but represent one of the most dramatic physical transformations in stellar evolution. The outer layers begin to expand, not quickly, not in any way that would register over a human lifetime, or 10 human lifetimes, or 1,000, but over millions of years, the outer envelope of the star drifts outward, growing larger, growing cooler at the surface as the same energy is spread across a larger and larger radiating area, shifting in color from the yellow-white of middle age toward the long red wavelengths of a cooler, expanded surface. The star becomes a red giant. The scale of this transformation is worth sitting with for a moment. A star in its ordinary hydrogen burning phase occupies a sphere roughly the size of the Sun, 1,000,000 kilometers across, large enough that 1,000,000 Earths could fit inside. The red giant that emerges from the expansion of that same star is hundreds of times larger still. If the Sun became a red giant today, and in roughly 5 billion years it will, its surface would extend outward past the orbit of Mercury, past the orbit of Venus. It would reach, by some estimates, nearly as far as the orbit of Earth itself, swallowing the inner solar system in a gradual, silent expansion that would take millions of years to complete. The Earth, if it survived, and the question of whether it does is still debated, would be immersed not in space, but in the attenuated outer atmosphere of the Sun itself. The distinction between inside and outside the Sun would dissolve. Imagine that expansion from the surface. In any given year, no movement is perceptible. The Sun looks the same. A century passes. Still nothing visible changes. 1,000 years. 10,000. The reddening at the horizon is barely there yet. But across 1,000,000 years, the disk in the sky has grown. Across 10 million years, it fills a larger arc. There is no moment of crisis. There is only the slow, patient swelling, the steady reddening, the gradual dimming of morning and evening into something rust-colored and enormous. Beneath the expanding envelope, the helium core continues to contract under gravity. It is not generating energy, but gravity is squeezing it, and squeezing raises the temperature. The core grows hotter as it grows smaller and denser, pressing the helium nuclei closer together. The outer layers are enormous and red. The core is small, dense, and becoming very hot. For a long time, millions of years, this process continues, the core contracting and heating, the envelope expanding, the helium sitting in the core and accumulating density. Then the core reaches approximately 100 million degrees. At that temperature, helium nuclei begin to fuse with each other. 3 helium nuclei, moving fast enough, pressed close enough, can merge to form a single carbon nucleus. This is the triple alpha process, named for the 3 helium nuclei, each of which is also called an alpha particle, that combine to produce the carbon. It is the origin of every carbon atom that has ever existed, in stars, in the interstellar medium, in the atmosphere, in the cells of every living thing that has ever grown on this planet. The carbon was made here, in this process, in the cores of red giants that died long before the sun existed. But the helium flash, as the sudden ignition of helium fusion in the degenerate core is called, does not announce itself to the outside universe. The core at this stage is degenerate. The electrons within it are packed so tightly that they have entered a regime where ordinary thermal expansion no longer governs their behavior. In normal matter, when you heat something, it expands, and the expansion carries the heat away and prevents a runaway. In degenerate matter, that self-regulating mechanism is absent. The pressure does not depend on temperature in the same way. So when helium fusion ignites in the degenerate core, the energy released does not cause the core to expand and cool. It simply heats the core further, which increases the fusion rate, which heats the core more, which increases the fusion rate again, in a loop that runs away in seconds. The energy released in that runaway is equivalent, briefly, to the combined luminosity of 100 billion suns. It is one of the most energetic events in the life of a sun-like star, and none of it reaches the surface. Every joule of that energy is absorbed by the vast, opaque outer layers of the red giant surrounding the core. The helium flash is entirely invisible to any observer outside the star. The star's surface does not brighten, it does not pulse, nothing is emitted. The energy is simply swallowed by the envelope, and the runaway burns itself out as the core lifts out of degeneracy and normal thermal regulation resumes. What follows is a more stable phase of helium core burning that carries no drama, only the slow consumption of the helium reserve. A star on this path has many more chapters. After the central helium is exhausted, the same pattern repeats at a larger scale. The carbon-oxygen core, because some of the helium has fused further to produce oxygen in a follow-on reaction, becomes inert. Helium shell burning resumes around the core. Hydrogen shell burning continues above that. The star ascends what astronomers call the asymptotic giant branch, a second phase of red giant evolution in which the outer envelope grows even larger, and the inner structure becomes a nested set of burning shells around the cooling core. On the asymptotic giant branch, the star develops a pulse. It is not a rapid pulse. Nothing in stellar evolution is rapid on human timescales. The pulse arrives every 10,000 to 100,000 years, a thermal instability in the helium-burning shell that causes it to flare briefly and then subside. Each pulse drives a wave of mixing through the interior. The convective currents that carry heat outward from the burning shells extend their reach, dipping down into regions that were previously stable and stirring carbon and other products of helium fusion upward into the outer layers of the star. This mixing carries the signature of what the star has been doing in its interior for billions of years, the carbon synthesized in the triple alpha process, and elements heavier than iron built through the slow neutron capture process, element by element, in the deep interior, up through the envelope, and eventually in the mass loss winds that pour from the star's bloated outer layers into the space around it. The material leaving the star in this phase is not merely hydrogen and helium, it is enriched. It carries iron and barium, and strontium and cerium, and zirconium, elements built up slowly through the capture of neutrons by lighter nuclei deep inside the star, a process that takes thousands of years per element, piling mass onto atomic nuclei, one neutron at a time, until they are heavier than anything that could have formed in the early universe. These elements drift outward in the stellar wind, mixing into the cloud of gas surrounding the star, eventually dissolving into the interstellar medium and becoming part of the raw material from which the next generation of stars will form. The star, in this phase, is generous with itself in the way that dying things sometimes are. It gives back. The winds from an asymptotic giant branch star can be strong. The star sheds mass at a rate that, over the course of the phase, amounts to a significant fraction of its total mass, returning to space material that has been locked in the star since it formed, processed and enriched by billions of years of nuclear burning, carried back out into the galaxy to drift and cool and eventually join new clouds of gas and dust. The outer envelope, loosened by the thermal pulses and driven outward by radiation pressure on the dust grains that condense in the cooling wind, streams away in an expanding shell. The star is dismantling itself from the outside in. What remains at the center is the carbon-oxygen core. The core is small, dense, hot from the energy of the shells that were burning around it, but no longer burning itself. The temperatures and pressures at the center of a sun-like star are never sufficient to ignite carbon fusion, which requires far higher conditions than helium fusion. The core simply sits at the center as the envelope departs, slowly exposed as the surrounding material thins and moves away. It is not large, perhaps comparable in volume to the Earth, though vastly denser, and it is extraordinarily hot. As the last of the outer envelope streams away, the exposed core begins to illuminate the gas around it. The core's surface temperature at this point may be well above 100,000 Kelvin, hot enough to emit in the ultraviolet, hot enough that the photons it releases carry enough energy to strip electrons from the atoms in the surrounding nebula, ionizing the gas and causing it to glow. The shell of material that was once the star's outer envelope becomes, over thousands of years, a glowing nebula of ionized gas, a structure that can extend across light years, expanding outward at tens of kilometers per second, thinning as it goes, but its light fading as the density drops and the gas recombines. In the 18th century, an astronomer named William Herschel observed these structures through the telescopes of his time and noticed that they looked, to him, somewhat like the disk of a planet, round, slightly extended, not the sharp point of a star. He called them planetary nebula. The name has nothing to do with planets. There are no planets inside a planetary nebula, no planetary processes at work. It was simply the best analogy available to a man with the instruments of his era, and the name stuck, as names do. The forms these nebula take are extraordinary in their variety. Some are nearly spherical, perfect shells of gas expanding symmetrically outward from the central star. Some are elongated into bipolar structures, two lobes extending in opposite directions, shaped by magnetic fields or the influence of a binary companion, deflecting the outflowing wind. Some have concentric rings, evidence of multiple episodes of mass loss at different rates. Some show complex internal structures, fingers of denser gas, bright arcs, dark lanes, carved by the interaction of the fast, thin wind from the hot central star ramming into the slower, denser wind shed earlier in the asymptotic giant branch phase. Each one is the record of the final centuries of a stellar life, written in glowing gas and expanding silently across the local interstellar medium. Stand inside one in thought. The surrounding gas is tenuous beyond ordinary measure, thinner than any vacuum achievable in a laboratory on Earth. Yet it glows. It glows because the ultraviolet light from the hot stellar remnant at the center is energetic enough to excite the electrons in the sparse atoms of oxygen and nitrogen and hydrogen, and when those electrons fall back to lower energy states, they release light at very specific wavelengths. The red of hydrogen, the blue-green of doubly ionized oxygen, the deep red of nitrogen. The nebula glows in colors that cannot all be seen with the naked eye, that reveal themselves fully only to instruments built to detect specific wavelengths, and that encode in their relative brightness the temperature and density and composition of the gas. And the gas is moving. Everything in a planetary nebula is moving outward, all the time, at speeds that human engineering cannot yet match. The expansion of the nebula is the last chapter of the star's visible story, the envelope spreading across space, thinning, cooling, the glow fading as the central star's ultraviolet output falls, and the gas becomes too diffuse to emit efficiently. Over tens of thousands of years, the nebula dissolves into the surrounding interstellar medium. It becomes invisible. The material does not cease to exist. It becomes part of the diffuse gas between the stars, slowly stirred back into the larger pool from which new stars eventually form. What remains behind when the nebula has gone is the smallest, densest, quietest part of the entire story. A planetary nebula, at its peak, is one of the more visually arresting objects in the night sky, if the instruments are sensitive enough to reveal it. The colors are rich, the structure is complex, the whole thing is expanding and evolving on timescales a human observer can follow, if that human observer happens to have an excellent telescope and unlimited patience. And at the center of this glowing, expanding structure, barely visible against the brightness of the surrounding gas, sits the remnant of the star that created it all. It is small. It is dense. It glows not from fusion, but from residual heat, the heat accumulated over billions of years of burning, now simply radiating into space from a surface smaller than the Earth's. It will continue to radiate for a very long time, not because anything new is happening inside it, not because any new fuel is being consumed, simply because it is hot, and hot things radiate, and the heat stored inside it is vast, and the rate at which it can escape through the thin insulating layers above the dense interior is slow. The nebula dims, the glowing shells of gas spread outward and thin and cool and fade, and as they fade, the silence they leave behind grows. The material that was once the star's outer envelope, the hydrogen-rich layers that were part of the star for billions of years, that saw the hydrogen burning phase and the red giant phase and the thermal pulses and the dredge-up events that carried carbon to the surface, all of it is now free, drifting outward through the interstellar medium, eventually to be incorporated into new molecular clouds, new protostellar disks, new generations of stars, and possibly planets. And in the quiet space where the nebula was, after the last of the glow has gone, the remaining object simply radiates, slowly, steadily, cooling across timescales that make the stellar life that preceded it seem brief. It does not burn. It does not expand. It does not pulse. The long, patient, geological slowness of the main sequence was itself merely a prelude to this, the still point at the end of all that process, the quiet thing that remains when all the drama has been spent. There is a way in which the whole stellar life, seen from a distance of sufficient time, looks like a preparation for this moment. The hydrogen burning built the helium flash built the carbon, the thermal pulses stirred the carbon and the heavy elements upward and returned them to space. The planetary nebula cleared the outer layers away. Each phase was a kind of processing, a kind of refinement, the star taking in the simplest raw material the universe began with and working it over billions of years into something more complex before releasing nearly all of that complexity back into the interstellar medium. What it kept, in the end, is the dense carbon-oxygen remnant at its center, held together by a force that has nothing to do with fire. There is also a way in which each phase, taken on its own, was complete. The main sequence phase was not merely a preparation for the red giant. It was itself a long, stable, luminous era, billions of years of steady emission that warmed planets and drove chemistry, and in the case of our own sun, made possible everything that has ever happened on the surface of the Earth. The red giant phase was not merely a passage to the planetary nebula. It was itself an era of enrichment, carrying newly forged elements toward the surface and out into space. Each chapter was its own thing. The story does not require a resolution to have had meaning in its earlier parts. The carbon and heavy elements that were stirred upward during the asymptotic giant branch thermal pulses are now somewhere in the interstellar medium. They are in molecular clouds. They are in the envelopes of younger stars. They are in the rocky material of planetary systems that formed after the star that made them was long gone. Some fraction of what was once the core of a dying star is now in the crust of a planet somewhere. Some fraction of the slow neutron-captured barium and strontium that rose through convective columns over thousands of years is now part of a mineral vein in a rock on some world that orbits another star. The connection between stellar evolution and planetary geology is not metaphorical. It is chemical. The elements needed to build a rocky planet were made in exactly these processes over billions of years in the interiors of stars that no longer exist. Consider the path of a single carbon atom. It began as helium, as two helium nuclei that fused in the triple alpha process in the degenerate core of an asymptotic giant branch star, releasing energy in the helium flash, becoming carbon in the conditions of 100 million Kelvin. It sat in the core as the star continued burning. In a thermal pulse, convective currents carried it upward through the stellar interior, through layers of hydrogen and helium, toward the outer envelope. The stellar wind carried it outward, away from the star, into the expanding shell of the planetary nebula. The nebula dissipated, and the atom drifted into the interstellar medium. Over millions of years, it became part of a molecular cloud. The cloud collapsed slowly under its own gravity. A protostellar disk formed. A star ignited at the center. And around that star, grains of dust accreted into pebbles, and pebbles into rocks, and rocks into planetesimals. And one of those planetesimals eventually became part of a planet. If that planet developed the conditions for organic chemistry, that carbon atom may have passed, eventually, into a molecule that carried information, into something that organized itself, into something that, given enough time, might have looked up at the sky. The star that made that carbon is not there to be seen anymore. Its planetary nebula faded tens of thousands of years ago. The white dwarf at its center has been cooling for billions of years, dimming slowly in the infrared, surrounded by silence. The light from the nebula has long since dispersed into the interstellar medium, too faint and diffuse to form an image in any telescope. What remains visible, if the instruments are precise enough, is that small hot object at the center of where the nebula was. It is not large, against the scale of what it once was, the red giant that could have swallowed several inner planets, the glowing shell of ionized gas that stretched across light years. It is almost nothing, but almost nothing in this context is still a solar mass of matter compressed into a sphere smaller than the Earth, radiating steadily from a surface heated to tens of thousands of Kelvin, slowly cooling, slowly dimming, carrying within it the thermal memory of a nuclear burning history that lasted longer than the age of the solar system. The planetary nebula that once surrounded it expanded outward and faded and thinned and became part of the background of the galaxy. The expanding shells of ionized gas spread at tens of kilometers per second until they were indistinguishable from the general diffuse interstellar medium. The colors faded, the red of hydrogen, the blue-green of oxygen, replaced by simple darkness, and the faint, uniform glow of background starlight. In that silence, in the space where the nebula was, the white dwarf continues to radiate. It does not know it has arrived. It has no interior monologue, no awareness of the billions of years behind it, or the billions of years of slow cooling ahead of it. It simply is. Hot, dense, quiet, no longer burning, no longer expanding. Arrived at a simplicity that the long stellar life that preceded it never quite had. A state of matter governed not by fire, but by the quantum behavior of its own compressed electrons. The nebula is gone, the glow has dispersed. The enriched gas has joined the galaxy's general pool of material, where it will wait for millions of years, perhaps hundreds of millions, before gravity gathers it again into new clouds, new stars, new systems. The atoms that were returned to space will be used again. The carbon and the heavy elements will find new homes. The hydrogen, returned from the outer envelope, will eventually fuel a new star. And the remnant left behind, the white dwarf, sitting in the silence where the nebula was, cooling across time with the patience of stone, is not an ending so much as a long pause, the last warm thing in a space that has grown quiet around it, a point of faint light in the dark, still radiating, still carrying the heat of everything it once was. The glow of the planetary nebula fades slowly. It fades the way the last light of a long day fades, not suddenly, but in degrees, each degree smaller than the last, until the eye can no longer trace the boundary between what remains and what is simply the dark of space. And in the quiet that comes after, small and dense and steady, the remnant holds its heat and radiates unhurried into the surrounding dark. A single solar mass of matter sits inside a sphere no wider than the Earth. There is no fire in it. There is no fusion. Nothing burns. The object generates no energy of its own, holds no reaction, contains no process that would announce itself to any instrument tuned to look for activity. From the outside, it is almost featureless, a pale point of light cooling so gradually that across a human lifetime, its surface temperature would not register any measurable change. And yet inside that small, quiet sphere, the pressure at the center exceeds anything a human analogy can comfortably hold. Every cubic centimeter of its interior contains roughly a ton of matter. The atoms that once built the outer layers of a living star have been compressed into a volume so small and held together so tightly that the ordinary rules governing the behavior of electrons no longer quite apply. And this is the white dwarf, Not a diminished star, not a smoldering remnant in the way a coal is a remnant of a fire, but something genuinely new, something governed by physics that has no analog in any object large enough to see with the naked eye. To understand what holds it up, it helps to begin very small, smaller than the atom. Inside the compressed interior, electrons are packed so close together that they begin to resist. Not because they are hot, not because they carry charge, but because of something more fundamental and stranger than either of those things. Two electrons cannot share the same quantum state. It is not a rule imposed from outside. It is woven into what an electron is. When matter is compressed tightly enough, the electrons fill all available states, and there is nowhere left for any of them to go. The resistance they generate from this quantum crowding is called electron degeneracy pressure, and it pushes back against gravity with a force that has nothing to do with temperature. The white dwarf could cool to absolute zero, and this pressure would not diminish. It is structural. It is permanent in a way that fusion-driven pressure never was. A star like the sun holds itself up by burning. Stop the burning and the support ends. A white dwarf holds itself up simply by existing in a compressed state. The electrons refuse to be pushed further together, and that refusal is enough. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth. Not because any of the atoms are exotic, they are mostly carbon and oxygen, the same elements in the air and in every living thing, but because they are packed into a space many thousands of times smaller than they would normally occupy. The space inside an atom, which in ordinary matter is almost entirely empty, has been squeezed away. What remains is something closer to a solid, made entirely of nuclei and electrons pressed hard against each other with almost nothing between them. It would sit inert on a table, generating no heat, no light, no reaction. It would be supported not by fire, but by the quantum refusal of its electrons to share any more of what little space remains. The interior of a white dwarf is composed mostly of carbon and oxygen. These are the end products of the nuclear reactions that ran in the star's core and intermediate shells during its long life, helium fusing 3 at a time into carbon, and then some of that carbon capturing another helium nucleus to become oxygen. By the time the outer layers have drifted away and the white dwarf is exposed, the deep interior is a roughly equal mixture of carbon-12 and oxygen-16 nuclei swimming in the sea of degenerate electrons that both supports the structure and carries heat. The nuclei themselves are positively charged ions moving in that electron sea, and the behavior of those ions over billions of years is one of the quietest and most profound things a white dwarf does. At first, when the white dwarf is young and still hot, the ions move freely. The interior is a dense fluid, the nuclei drifting in loose disorder through the electron sea, the whole system slowly losing heat through the thin atmosphere above. Centuries pass, millennia pass, the surface cools by a few degrees. The interior follows, slowly, because the core is so thermally massive that it takes vast stretches of time to communicate any change to the surface. The cooling is not dramatic. It leaves no trace a casual observer would notice. It is a process measured not in years, but in billions of years, and what it eventually produces is one of the most ordered structures in the universe. As the core temperature falls toward approximately 10 million Kelvin, something begins to change in the behavior of the carbon and oxygen ions. They are no longer moving freely enough to resist the electromagnetic pull between them. The ion that has been drifting begins in some small region to settle. Another ion settles next to it, and the geometry of the electromagnetic force means there is one arrangement that is slightly lower in energy than all the others. The ions begin to lock into a crystalline lattice, not ice, not glass, not any crystalline substance familiar from ordinary experience, but something denser and more orderly than any of those things, built from atomic nuclei themselves rather than from whole atoms. Carbon and oxygen ions arranging themselves into a rigid periodic structure in the deep interior of a cooling stellar remnant, surrounded by the electron sea that continues to move freely even as the ions freeze in place. This crystallization begins at the center, where the pressure is highest and the density is greatest. It does not happen quickly. Nothing about a white dwarf happens quickly. The crystallization front spreads outward from the center, the way a frost might spread from the inside of a glass, outward to its edge. Slowly, ion by ion, the ordered region growing at a rate that would be invisible over any time scale a human life could encompass. Over hundreds of millions of years, the crystalline region expands. Over billions of years, it reaches toward the middle layers of the interior. The white dwarf is slowly becoming, from the inside out, a crystal the size of the Earth. The process is not simply geometrical. When a substance crystallizes, it releases energy. The transition from disordered fluid to ordered solid is thermodynamically downhill, and the energy given up in the process has to go somewhere. In the white dwarf interior, it becomes heat that flows outward through the interior and eventually into the thin atmosphere, and from there into space. This is called latent heat, and its release during crystallization means the white dwarf cools a little more slowly through that phase than it would otherwise. The cooling curve, which would otherwise be a smooth and steady decline, develops a shallowing, a region where the temperature drops more slowly because the crystallization is quietly supplementing what would otherwise be an uninterrupted loss. For roughly 1 billion years or more, this hidden energy release acts like a slow, deep exhale within the interior, holding the white dwarf marginally warmer and marginally brighter than its age alone would predict. This was a theoretical prediction for decades before it could be confirmed. The idea that white dwarfs should pause in their cooling due to crystallization had been worked through mathematically, and the physics was coherent enough that most researchers accepted it as almost certainly real. The observational proof required a data set precise enough to resolve the cooling sequence of white dwarfs in detail, a census of these faint objects spread across a region of the sky, measured with enough accuracy to see not just individual white dwarfs, but the statistical shape of their distribution in temperature and luminosity. That proof arrived in 2019 when the Gaia Space Telescope released a catalog of stellar positions and brightnesses detailed enough to reveal something strange. A clustering of white dwarfs appeared on the cooling sequence at temperatures consistent with the crystallization phase. More white dwarfs than expected at a certain brightness, as if they had accumulated there, held in place by the extra energy their interiors were releasing. The excess was real. The pause was real. The crystallization that had been predicted from first principles was written plainly into the distribution of 10,000 dying stars. Now move outward from the crystallizing center, past the deep carbon-oxygen interior, through the intermediate layers toward the surface. The transition from the dense interior to the atmosphere of a white dwarf is one of the sharpest boundaries in nature. The interior is enormously dense, the nuclei packed close, the electrons degenerate and quantum mechanical. The atmosphere, by contrast, is nearly nothing. In mass terms, the observable atmosphere of a white dwarf makes up less than 1 part in 10,000 of the total. Everything a telescope can see, every spectral line, Every measurement of what elements are present, all of it comes from a layer that contains almost none of the total mass of the object. The white dwarf presents its atmosphere to the universe like a membrane, thin and precisely ordered, laid over an interior it almost entirely conceals. What orders this thin layer is gravity. The surface gravity of a white dwarf is approximately 100,000 times stronger than the gravity at Earth's surface. On such a surface, anything heavy sinks and anything lighter floats, and the separation happens fast. Helium is heavier than hydrogen, so hydrogen floats above helium. Heavier elements, carbon, oxygen, calcium, iron, sink below both, pulled downward toward the interior by the relentless pressure of that enormous gravitational field. Over relatively short timescales, short by stellar standards, which means anything from a few days to a few million years, depending on the temperature, any heavy elements present near the surface should settle into the interior and disappear from view. A pure hydrogen atmosphere should be what remains on top. White dwarfs with hydrogen-dominated atmospheres are classified as Da white dwarfs, and they make up roughly 3/4 of all known white dwarfs. Their spectra are nearly featureless, showing broad hydrogen absorption lines and almost nothing else. Beneath that thin hydrogen layer, in most cases, lies a thinner layer of helium. The helium that was present in the outer envelope has settled below the hydrogen over time. And beneath the helium lies the vast carbon-oxygen core, invisible to any instrument, its presence inferred rather than observed. The surface tells almost nothing of what lies below. The atmosphere is a thin mask over a dense and ancient interior, organized by gravity into a precise vertical layering that would persist without disturbance for as long as no external material disturbed it. Some white dwarfs have helium-dominated atmospheres rather than hydrogen. These are classified as Db white dwarfs, and the reason some objects show hydrogen and others show helium above the surface is still a matter of active investigation. The detailed physics of the atmospheric transition and what determines which element ends up on top in any given case touches on processes of mixing, accretion, and the subtle behavior of fluids under extreme gravitational fields. The broad picture is clear enough. Gravity stratifies, the lightest element rises, and the surface presents to the universe whatever happens to dominate that lightest layer. Hold in mind now the full picture of what has been built, a sphere roughly the size of the Earth, massing near a solar mass, held together by the quantum pressure of its degenerate electrons, its deep interior, a slowly crystallizing lattice of carbon and oxygen ions, its thin atmosphere stratified by gravity, so powerful that no human intuition about buoyancy or settling has any direct analog for it. No energy is being generated, no reactions are running in the core. The object is simply cooling slowly across billions of years through the long patience of the universe. The relationship between mass and size in these objects is one of the more counterintuitive facts in astrophysics. Ordinary experience teaches that adding mass to an object makes it larger. A bigger star is more massive than a smaller one. White dwarfs behave the opposite way. Add mass to a white dwarf and it shrinks. The reason lies in the physics of the degenerate electron pressure that supports it. As more mass is added, the electrons are compressed into less space, and in that compression they are forced into states of higher and higher momentum. When the electrons approach relativistic speeds, speeds close to the speed of light, the relationship between their momentum and the pressure they exert changes in a subtle but crucial way. The pressure they provide grows more slowly than the gravity above them. The balance tips, and the equilibrium settles at a smaller radius. Subramanian Chandrasekhar worked out the mathematics of this in 1930. He was 19 years old, traveling by ship from India to England, and during that voyage, he carried through the calculation that incorporated special relativity into the equations governing white dwarf structure. What emerged from his work was not just a curve relating mass to radius, it was the existence of an upper limit. As the mass approached a certain threshold, the relativistic correction to the electron pressure became increasingly severe, and the predicted radius shrank towards zero. There was a maximum mass above which no white dwarf could exist. Not because of any dramatic instability, but because at some point, the relativistic softening of the electron pressure would allow gravity to win outright. That maximum mass sits at approximately 1 4/10 solar masses, and it is now called the Chandrasekhar limit. The mass-radius relationship that follows from his work has been confirmed observationally, most cleanly using white dwarfs in binary star systems, where the mass can be measured independently from the orbital dynamics. White dwarfs of higher mass are indeed smaller. A white dwarf of 1.2 solar masses is physically smaller than a white dwarf of half a solar mass, compressed into a tighter sphere by the weight of the extra material above it. A white dwarf near the Chandrasekhar limit is only a few thousand kilometers across, smaller than the Earth, squeezed by the additional mass into a denser, tighter object than its lighter siblings. Chandrasekhar presented his results at a meeting of the Royal Astronomical Society in January of 1935. Arthur Eddington, the most eminent astrophysicist of the time, rose after the presentation and dismissed the calculation. He argued that the result was physically absurd, that nature could not permit such a thing as a stellar remnant with no stable equilibrium, and his authority was enough to ensure that the idea would wait. Chandrasekhar moved on to other problems. He continued working in astrophysics for decades, contributing to the understanding of stellar structure, radiative transfer, and black holes. In 1983, more than 50 years after that sea voyage, the Nobel Prize in Physics acknowledged what the voyage had produced. The inverse mass-radius relationship has a texture to it that is worth sitting with. In most structures, more material means more volume. A pile of sand grows taller as you add sand. A star expands as its mass increases at formation. In a white dwarf, the added mass goes somewhere else entirely. It goes not into width, but into density. The structure becomes not bigger, but heavier, not larger, but tighter, not more expansive, but more compressed. The more massive the white dwarf, the smaller the sphere that holds it, the greater the weight pressing on the electrons, the more those electrons are squeezed toward relativistic velocities, the more their pressure softens relative to gravity, and the closer the object settles to the limit beyond which no equilibrium remains. This is the internal portrait of a white dwarf at its most complete: dense, crystallizing, stratified, cooling, smaller than the Earth and more massive than the Sun, generating no energy, losing heat through a thin atmosphere only slowly, supported not by any active process, but by the passive structural resistance of its quantum mechanical interior. There is a quality to this object, not of struggle, not of activity, but of having arrived at something settled and permanent. It has passed through the extraordinary violence of stellar evolution and emerged on the other side as something very quiet. The quiet is worth dwelling on. A star at the height of its life is continuous activity. Photons born in the core scatter outward through the dense interior on paths so tortured that a single gamma-ray photon can take hundreds of thousands of years to work its way from the site of its creation to the surface. Convection stirs enormous volumes of gas through turbulent cells. The surface heaves with granulation and flare, and the constant reprocessing of energy rising from below. All of that is gone. The white dwarf surface is still. The interior is still, or becoming still, as the crystallization front advances outward. The only process at work is the slow loss of stored thermal energy through the surface, heat that was accumulated over the star's entire earlier life, now leaking away one photon at a time across billions of years. There is something in the physics of electron degeneracy that bears approaching from another direction, because the way it works is unlike anything in ordinary experience. In a gas, pressure depends on temperature. Heat a gas and it pushes harder. Cool it and it softens. This is familiar from every pressure vessel, every balloon, every tire. In a degenerate gas, this relationship no longer holds. The pressure comes not from the thermal motion of the particles, but from the quantum constraint on how close those particles can be. No two electrons can share the same quantum state. When electrons are packed tightly enough, all the low energy states fill up, and the only remaining states are high energy ones. The electrons are forced into those states, not by being hot, but by having no other place to be. And electrons in high energy states exert pressure. If the temperature falls, the pressure does not fall. The electron degeneracy pressure of a white dwarf's interior is almost entirely independent of temperature, at the temperatures and densities found in these objects. The white dwarf could cool and cool further, and the support holding it up would remain. This is the reason a white dwarf is permanent in a way that a star is not. A star held up by pressure, depending on thermal energy, will collapse if its energy source fails. A white dwarf held up by electron degeneracy pressure will remain stable regardless of what happens to its temperature. There is a limit, of course. The Chandrasekhar limit is that limit. But within the range of masses where white dwarfs exist, the support is essentially absolute. The structure is not burning itself up to stay aloft. It is simply there, held in place by the rules of quantum mechanics, cooling slowly and without drama toward an endpoint that remains for every white dwarf formed in the present universe, still billions of years in the future. The surface layers of a white dwarf are worth examining with some care, because they are the interface through which everything knowable about the interior is mediated. What a telescope sees is the photosphere, the layer from which light can finally escape. And in a white dwarf, this layer is extraordinarily thin. Not thin by stellar standards, but thin in absolute terms, a layer perhaps tens of kilometers deep, above a sphere thousands of kilometers across. The entire observable atmosphere is less than a fraction of a percent of the total radius, and its mass, as noted, is a vanishingly small fraction of the total. Within this thin layer, hydrogen sits on top in the DA white dwarfs that make up most of the population. Below it, in many objects, lies a helium layer, perhaps a few hundred kilometers deep. Beneath that, the transition to the dense carbon-oxygen interior. The layers are held apart by gravity, so precise and so powerful that diffusion timescales become geologically meaningful. Hydrogen floats. Helium sinks slowly through the hydrogen. Heavier elements sink faster, disappearing into the interior on timescales of days in hot white dwarfs or millions of years in cool ones, depending on the temperature and the viscosity of the fluid layers above the degenerate core. In a DA white dwarf around 50,000 Kelvin, a calcium atom introduced near the surface would sink below the observable photosphere in a matter of days. The gravitational settling is that efficient. In a cooler white dwarf, around 12,000 Kelvin, the same atom might persist for tens of thousands of years before sinking out of view. The difference arises from the temperature-dependent structure of the layers above the degenerate core, layers that become more viscous and more resistant to diffusion as they cool, slowing the settling process without ever preventing it entirely. The iron rule is that heavy elements always sink and are always eventually lost, the atmosphere purifying itself over time toward whatever lightest element is present. This purification, which sounds like an elegant simplification, is in fact one of the most scientifically productive features of white dwarfs, though the reasons for that belong to a separate consideration. For now, what matters is the picture, a surface of extraordinary gravitational intensity, organizing whatever material is present into precise vertical layers, with hydrogen or helium on top, and everything else pulled below, the whole thin envelope sitting over a dense and ancient interior that no direct observation can access. The complete object, then, is a layered thing. At the center, a crystalline lattice of carbon and oxygen ions, growing outward through the deep interior at a rate that would take billions of years to reach the outer regions. Surrounding that crystalline core, a region still in fluid state, the carbon-oxygen ions still mobile enough to move, the electrons still flowing freely around them, the whole region conducting heat outward toward the surface slowly. Above that fluid interior, the thin, non-degenerate layers, helium, and above that the pure hydrogen atmosphere, all of it held in precise gravitational order by the enormous surface gravity. And at the surface, a photosphere radiating away stored heat into the surrounding space, slowly enough that even after 10 billion years of cooling the temperature at the surface remains thousands of Kelvin. There is a quality of compression in the white dwarf, not just physical compression, but a kind of temporal compression, the way an entire stellar life is distilled into something small and still. The star that became this white dwarf burned hydrogen for billions of years, expanded into a giant fused helium in its core, built up carbon and oxygen through the triple alpha process, and then shed its outer layers in a slow luminous wind before the core was exposed. All of that history is encoded in the object that remains. The carbon and the oxygen in the deep interior are the direct products of the nuclear reactions that the star ran in its final phases. They carry in their ratios and in their distribution the record of a life too long to imagine and too quiet in its final form to easily notice. A sphere the size of the Earth, a solar mass of compressed matter, an interior becoming slowly a crystal, an atmosphere thinner than most atmospheres anywhere, stratified with an exactness that has no parallel in ordinary nature, no energy being made, no reactions running, just stored heat leaking outward through quantum-supported density and a thin, bright surface into the space that surrounds it. Hold still in that image for a moment. The interior is not in turmoil. The electrons are not doing anything dramatic. They are simply filling the only states available to them, as they always have, as they will for as long as the object exists. The ions in the crystallizing core are not being driven into order by any outside force. They are settling, the way anything settles when the energy to remain disordered is no longer available, finding the configuration that requires the least. There is something almost geological in it, the same slow ordering that turns a supersaturated solution into a crystal or a hot silica melt into obsidian glass, except that the material is atomic nuclei and the forces are electromagnetic and the timescales are not geological but cosmological. The crystallization that began at the center will continue outward, very slowly, for as long as the interior remains above the relevant temperature threshold. That threshold retreats inward ahead of the cooling front for a time, and then as the center crystallizes, it moves outward. The crystalline region grows, the fluid region shrinks. Eventually, in a time so far ahead that no human construction of time easily spans it, the entire interior will have passed through the transition. The ions will all be locked in their lattice. The latent heat will have been fully released and spent. The white dwarf will have become, in its deep interior, a rigid and ordered thing, an enormous crystal made of stellar ash, smaller than the Earth and quietly cooling toward temperatures that no longer make light. But that endpoint is still far ahead for every white dwarf that exists. For now, somewhere between the still-forming crystalline center and the radiating surface, the object holds its layered quiet. No fire, no burning. Just the slow release of heat stored in matter that was once the core of a star, passing through layers of compressed carbon and oxygen and thin atmospheric hydrogen, disappearing finally into the cool dark of interstellar space, one photon at a time. The crystallization front, at this moment, is somewhere inside the deepest layers of the interior. It is moving outward so slowly that to call it movement is almost misleading. It is more like a gradual change in state, a settling into place of ions that had been mobile and are now not, the ordered region expanding into the disordered one, over periods of time that dwarf the age of civilizations. Over the next billion years, it will move outward. Over the next few billion, it will reach deeper into the middle layers. The latent heat it releases will flow upward, through the dense fluid regions above, through the thin atmospheric layers, out into space. The white dwarf will remain, during all of that time, marginally warmer and marginally brighter than it would otherwise be. The crystallization sustaining a faint excess of luminosity that only a very precise and very patient survey of many thousands of cooling stars could detect. And that is exactly how it was detected. The Gaia telescope, watching not one white dwarf, but tens of thousands, mapped their distribution across temperature and luminosity, with an accuracy fine enough to see the statistical trace of the crystallization pause, the accumulation of objects at certain temperatures, holding there longer than expected, releasing the latent heat of their freezing interiors into the patient record of the sky. The theory that had been worked out across decades and confirmed in 2019 by the distribution of 10,000 points of ancient stellar light. The white dwarf does not know it is beautiful in its physics. The ions do not arrange themselves in order for any purpose beyond the bare minimum energy configuration that the laws of electromagnetism require. The electron degeneracy pressure does not refuse to yield out of any principle. It refuses because quantum mechanics admits no other option. The gravity that stratifies the thin atmosphere into its precise layers does not organize. It simply pulls, and everything finds its own level in response to the pull. There is no will in any of this, no direction, no intention, only matter following the rules of the universe into a configuration that happens to be, from the outside, profoundly quiet. From the center, where the crystallization front moves outward through the dense lattice at its geological pace, all the way to the photosphere, where the last thin layer of hydrogen radiates heat into the surrounding dark. The white dwarf is a portrait of what matter does when the processes that animate it have finished. It does not collapse, it does not scatter, it settles into density, into order, into stillness. The crystal spreads slowly outward through the deep interior, ion by ion, across time so long and so quiet that even the universe seems not to notice. and the object cooling at the center of it holds the compressed memory of a living star, carrying it forward into the dark slowly and without urgency, for as long as the universe continues to allow such things to remain. In the middle of the Indian Ocean, on a slow steamship crossing from Madras towards Southampton, a young man sat at a small desk with a pencil and a stack of paper, working through equations by the light available to him. It was 1930. He was 19 years old. Outside the porthole, the water was dark and enormous and indifferent, moving in long swells that rocked the ship with the patient rhythm of something that had been doing this long before any ship existed. He had time, 18 days of ocean between him and England, and he used it the way a person uses deep quiet, going further into the work than ordinary distraction allows. His name was Subramanian Chandrasekhar, and what he was working toward, without yet fully knowing it, was a limit. The problem he was turning over concerned electrons. Deep inside a white dwarf, a stellar remnant the size of the Earth, carrying the mass of the Sun, electrons are packed so tightly that an ordinary quantum rule becomes the only thing standing between the star and its own gravity. That rule is simple at its root. No two electrons can occupy the same quantum state at the same time. Because of this, electrons resist compression with a kind of pressure that has nothing to do with temperature or heat. They push back not because they are warm, but because the laws of quantum physics leave them no room to do otherwise. This pressure, generated purely by the geometry of quantum states, holds the white dwarf open against the inward pull of all its own mass. For most purposes, this picture was considered stable. A white dwarf would press back against gravity and rest there, cooling slowly indefinitely. But Chandrasekhar had noticed something that the earlier treatments of the problem had not fully confronted. As electrons are compressed more and more tightly, they are forced into states of higher and higher momentum. At some point, that momentum begins to approach the speed of light, and when that happens, the relationship between momentum and energy changes. The stiffness of the quantum pressure softens. It does not vanish, but it weakens, just slightly, just enough. And in that slight softening, a crack opens in what had seemed to be an absolute wall. He worked through the mathematics on the ship, incorporating the equations of special relativity into the description of the electron gas inside a degenerate stellar remnant. The calculation was careful and slow, the pencil moving across paper in the particular rhythm of someone who is checking each step before committing to the next. What emerged was not a dramatic result, not a sudden collapse of certainty. It was a threshold, a precise value of mass, roughly 1 4/10 times the mass of the Sun, above which the softened relativistic pressure could no longer hold the structure together. Below that mass, the white dwarf was stable. Above it, gravity would win. The threshold carried no exceptions. It followed directly from the mathematics. Chandrasekhar arrived in England with the calculation in hand. He presented it over the following years, refined it, checked it against the known masses of observed stellar remnants, and found that it held. The threshold became known as the Chandrasekhar limit, and it described not merely a boundary for one class of objects, but an absolute constraint built into the nature of matter under compression. It said, there is a maximum mass beyond which no electron pressure, however strong, however dense, can prevent a stellar remnant from continuing to collapse. The universe, it turned out, had a ceiling on what a white dwarf could be. At the Royal Astronomical Society meeting in 1935, the most respected astrophysicist in England rose to dismiss the result. Arthur Eddington had measured the bending of starlight during a solar eclipse 16 years earlier and helped confirm the general theory of relativity in the process. He was not a man accustomed to being wrong about physics. He told the assembled scientists that Chandrasekhar's conclusion was absurd on its face, that a stellar remnant simply could not go on collapsing without limit, that nature must provide some stopping point, that the mathematics must be missing something. He said this with the full authority of his reputation, and several of the people in the room found his objection reassuring because it was offered with such certainty. Chandrasekhar did not abandon the calculation. He continued his work, pursued other lines of research, taught at the University of Chicago for decades, and waited. The objection was never given a physical basis. No mechanism was found that would save a sufficiently massive remnant from further collapse. The mathematics had been correct all along. In 1983, more than 50 years after the voyage on the Indian Ocean, Chandrasekhar received the Nobel Prize in Physics, in part for this work, for a result derived by lamplight on a moving ship by a 19-year-old who had been given briefly the gift of uninterrupted time. The limit does not exist only in equations. It manifests in the observable universe through the way white dwarfs age in binary star systems, two stars in orbit around one another, bound together by gravity, their fates intertwined across millions or billions of years. In these systems, the white dwarf does not always exist in isolation. It has a companion, and if that companion is close enough, and if the companion's own evolution causes it to expand and swell into a larger, more diffuse star, the white dwarf may begin to draw material from it. The process begins at a boundary that exists only in the mathematics of gravity, an invisible surface in space, shaped like a figure 8 laid on its side, where the gravitational pulls of the two stars exactly balance. This surface is called the Roche lobe, named for the French mathematician who first described it in the 19th century. When a companion star expands far enough to fill its own Roche lobe, material at the outer edge of the companion no longer belongs exclusively to it. Gas there sits at the precise point where the white dwarf's gravity pulls as hard as the companion's, and the balance tips slowly over geological stretches of time toward the white dwarf. That gas does not fall straight across. The rotation of the binary system gives it angular momentum, and so it spirals inward, forming a flattened ring of infalling material that circles the white dwarf before gradually descending to the surface. The ring glows. Its friction heats it to temperatures high enough to emit light, sometimes in the ultraviolet, sometimes in X-rays, depending on the rate of the infall. From a great distance, these systems are visible as sources of variable light, flickering as the disk shifts and the accretion rate changes. They are called cataclysmic variables because from time to time, the accumulation of material on the white dwarf's surface ignites in a brief thermonuclear flash, a nova, visible briefly as a new point of light in the sky, but the nova burns away only the surface layer. The white dwarf itself persists. What does not persist over long enough time is the white dwarf's mass. With each increment of gas drawn from the companion and settled onto the surface, the white dwarf grows slightly heavier. The additions are small. In the most active of these systems, roughly 1/10,000,000th of a solar mass per year. To gain even a tenth of a solar mass would take, at that rate, 1,000,000 years. To gain enough mass to matter to approach the Chandrasekhar limit from below would take far longer. But the universe is patient. Some of these systems have been accreting for hundreds of millions of years. The white dwarf gains mass the way a shore gains sediment, grain by grain, imperceptibly, the floor rising so slowly that nothing appears to change on any timescale a living thing could observe. Deep inside the white dwarf, the effects of the added mass accumulate differently from the way they manifest at the surface. The surface gains heat and hydrogen and shows nova flashes and brightness variations. The interior responds to something else entirely. The increase in total mass increases the gravitational pressure on the core. As the mass climbs, the core is squeezed tighter. The electrons inside are pressed into smaller volumes, pushed toward higher momenta, nudged incrementally closer to the relativistic regime, where Chandrasekhar's correction begins to matter. The star grows physically smaller as it grows more massive, each additional fraction of a solar mass pressing the interior into a denser, tighter, harder configuration. This is the inverse relationship that Chandrasekhar identified. More mass means a smaller star because the higher compression it generates forces electrons into relativistic states that cannot maintain the same volume. A white dwarf of half a solar mass is roughly the size of the Earth. One approaching the Chandrasekhar limit is considerably smaller, a few thousand kilometers across, its interior squeezed to a density that makes the material inside it more akin to the nucleus of an atom than to anything found in ordinary matter. And still the companion pours gas across the invisible boundary, and still the disk spirals inward, and still the mass climbs. At some point, as the mass approaches 1 4/10 solar masses, the core temperature and density reach a value that crosses a different kind of threshold. Carbon, packed into the white dwarf's interior from billions of years of earlier stellar evolution, begins to fuse. Under ordinary circumstances, a fusion reaction heats the material around it. The material expands, the reaction rate drops, and a kind of thermal regulation keeps the process controlled. But under conditions of extreme degeneracy, this regulation does not work. The electron pressure that supports the white dwarf does not depend on temperature. When the carbon begins to fuse and releases heat, the pressure does not increase, the star does not expand. The temperature climbs, and the climbing temperature drives the fusion rate higher, and the higher fusion rate climbs the temperature further. In fractions of a second, the reaction becomes a runaway. The entire interior of the white dwarf, a solar mass of carbon and oxygen compressed into a sphere the size of a small city, detonates. There is no gradual brightening. There is no early sign in the light curve that something is building. The star exists, and then in the space of a second, it does not. The thermonuclear explosion propagates outward through the white dwarf material faster than sound can travel through it. A detonation front carrying temperatures of billions of degrees that fuses the carbon and oxygen into heavier elements, nickel, cobalt, iron, in quantities that no other process in the universe produces so efficiently. The energy released is roughly 10 to the 44th joules. It is sufficient to blow the entire white dwarf apart. No remnant is left behind. This is a Type 1a supernova. The light it releases travels outward in all directions from the site of the explosion, a sphere of photons expanding at the speed of light through the surrounding space. From within the host galaxy, the event is for a time comparable in brightness to the combined light of every other star in that galaxy. Simultaneously, billions of stars, all at once, dimmed to nothing against a single point of destruction. Then, over weeks, the light fades. The nickel-56 forged in the explosion decays to cobalt-56, and the cobalt-56 decays to iron-56, and the energy released in those decays powers the brightness for a time before it too diminishes. The remains of the white dwarf, scattered heavy elements in a quickly expanding shell, disperse into the interstellar medium, over thousands of years, eventually becoming indistinguishable from the general enrichment of the galaxy. What makes Type 1a supernovae extraordinary as objects of observation is not the violence of the event, but the regularity of it. Because the explosion is always triggered at the same critical mass, the Chandrasekhar limit, the amount of energy released is nearly the same each time. The peak brightness of the explosion is within predictable corrections, a known quantity. An astronomer who sees a Type 1a supernova in a distant galaxy can measure how bright it appears at Earth and compare that to how bright it must actually be, and from the ratio of those two numbers, the actual luminosity and the apparent brightness, derive the distance to the galaxy with precision. The Type 1a supernova is a standard candle, a fixed light source whose actual intensity is reliably known. This property was recognized and calibrated across the 20th century, but it became the center of one of the most significant discoveries in modern science during the 1990s. Two independent groups of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to use Type 1a supernovae to map the expansion history of the universe. By measuring these events in galaxies billions of light years away and comparing their distances to the recession velocities of those galaxies, they intended to determine whether the universe's expansion was slowing, as gravity would demand, or remaining steady. What they found was neither. The distant supernovae were fainter than expected for their redshift, meaning they were farther away than the standard picture predicted. The universe was not slowing, it was accelerating. The expansion of space itself was speeding up. Some form of energy spread through the fabric of the universe and pressing outward against gravity on the largest scales was overcoming the gravitational pull of all the matter in the cosmos and driving the galaxies apart at an increasing rate. This substance, or this property of space, had no satisfactory explanation in physics at the time, and its nature remains, to this day, genuinely open. The name given to it was dark energy. Its existence was inferred, not from any direct detection, but from the distances written in the brightness of exploding white dwarfs in galaxies billions of light years away. The measurement was awarded the Nobel Prize in Physics in 2011. Consider what that means in terms of the chain of connection. An electron, deep in the core of a white dwarf, is pushed by the gravity of an accumulating mass toward a slightly higher momentum, a momentum so close to the speed of light that the quantum pressure it provides begins to soften. That softening, described in an equation worked out on a slow ship crossing the Indian Ocean, defines the mass at which a white dwarf will destroy itself. When the destruction happens, the uniformity of the critical mass ensures that the energy of the explosion is consistent enough to serve as a measuring rod across intergalactic space. And with that measuring rod, astronomers discovered that the space the light was crossing was not expanding at a constant rate, but at an increasing one, a discovery that changed the picture of what the universe is made of and where it is going. All of that carried in the light of a dead star. The light from a Type 1a supernova does not arrive all at once. When the explosion occurs in a galaxy that lies, say 500 million light years away, the photons released at the moment of detonation begin a journey that will take 500 million years to complete. They travel outward through the intergalactic medium, through a space that is expanding behind them as they go, in a silence so total and a darkness so complete that the concept of silence or darkness barely applies. There is no medium to carry sound. There is no nearby light source to cast shadow. The photons simply travel at the speed that light travels through the geometry of space-time, which is itself slowly changing around them as the universe expands. Along the way, the photons are shifted. The expansion of space stretches their wavelengths slightly, moving them toward the red end of the spectrum. By the time they arrive at Earth's telescopes, a careful measurement of this redshift reveals how much the universe has expanded since the light was emitted, which is itself a record of how long the light has been traveling, and therefore how far the source is. This redshift, combined with the intrinsic brightness of the supernova, is the measurement that allowed astronomers to discover that the universe is not decelerating. The information was encoded in the light at the moment of explosion, locked into the photon's wavelengths across 500 million years of travel, and read out at the end of a long night of observation by instruments sensitive enough to catch the difference between a universe that is slowing and one that is not. The difference they found was not large in absolute terms. It was the kind of difference that lives in careful calibration, in the comparison of numbers that are close but not identical, in a residual that only becomes meaningful when many supernovae are combined and the statistics are allowed to speak. But the residual was real. The supernovae were consistently a little too faint, placed a little too far. For a universe that was simply coasting, something was pushing, and the discovery of that something, dark energy, or whatever name will eventually describe it properly, is now one of the foundational results of modern cosmology. It rests on the Chandrasekhar limit. The limit rests on the behavior of relativistic electrons. The behavior of those electrons rests on the Pauli exclusion principle, a rule that emerges from the deep structure of quantum mechanics, from the fact that the universe has a specific and non-negotiable way of counting the states available to fermions. A 19-year-old with a pencil and 18 days of ocean turned that counting rule into a number 1 and 4/10 solar masses, and that number pressed outward through binary star systems and thermonuclear explosions and 500 million years of intergalactic travel, arrived at a set of telescopes and revealed that the universe is doing something no one had predicted. Not all white dwarfs in binary systems follow this path. The rate of accretion, the composition of the accreting material, the mass of the white dwarf at the start, the orbital separation of the binary, all of these vary. Some white dwarfs accrete slowly and shed mass episodically in novas without ever approaching the critical threshold. Some may merge directly with companion stars, rather than accreting gradually. The precise mechanism by which a given white dwarf reaches the conditions for a Type 1a explosion is still, in several of its details, a subject of careful study. But the outcome, when it occurs, is consistent. The critical mass is reached, the degenerate carbon ignites without restraint, and the star is gone. There is something in the geometry of this that invites a long pause. The white dwarf spent billions of years in formation, its progenitor star burning hydrogen on the main sequence across timescales measured in billions of years, then swelling into a giant and shedding its outer layers over millions more, then settling as a cooling remnant in the dark. It spent billions more years cooling, losing heat to space in a slow thermal exhale, its interior gradually crystallizing into ordered lattices of carbon and oxygen ions as its temperature fell. And then, in the final phase, it accreted mass from a companion across hundreds of millions of years, adding mass in increments so small as to be individually unmeasurable until the accumulated weight finally crossed the threshold defined by an equation on a ship. And then it ended in less than a second. The timescales involved, the billions of years of patience, the second of detonation, sit at extreme opposite ends of any scale a person might use to measure events. But the second does not cancel the billions of years. it follows from them. The explosion is the final consequence of every slow step that preceded it. The hydrogen fusion, the helium burning, the carbon-oxygen remnant, the cooling, the accretion, the rising mass. Each step was required for the next. The violence at the end was not imposed from outside, but generated from within, the natural conclusion of a sequence that had been running, step by step, since the star first formed. The light from that conclusion travels outward without a source anymore. Nothing remains at the site of the explosion to mark where the white dwarf stood. No neutron star, no black hole, no cooling remnant of any kind. The material is scattered, diffuse, spreading through the interstellar medium to become part of the next generation of stars and planets, and eventually the cores and shells and living tissues of whatever forms in the gas clouds that inherit it. The iron in the explosion becomes the iron in the next nebula. Time and gravity and chemistry will take it from there. Across intergalactic space, the light continues its travel. 500 million years for one event, a billion for another, several billion for the most distant supernovae in the surveys that discovered dark energy. The photons cross the space between galaxies, which contains almost nothing, a handful of hydrogen atoms per cubic meter, faint magnetic fields, the cosmic microwave background pressing in from all directions at the temperature of a few degrees above absolute zero. In this space, the photons are alone in a way that nothing on Earth can be alone. They carry information, the wavelengths that encode the redshift, the brightness that encodes the intrinsic luminosity of the event, and they carry it passively, without intention, without awareness, here across a duration that exceeds the entire span of complex animal life on Earth by orders of magnitude. Eventually, they arrive. A telescope on a mountaintop or in orbit above the atmosphere catches a fraction of them. A detector translates their energy into a signal. Software compares the signal against a catalog of known sources and flags a brightening point of light in a galaxy whose redshift has already been measured. An astronomer examines the data, confirms the spectral signature of a Type 1a event from the characteristic pattern of ionized silicon and iron in the spectrum, and records the peak brightness. That brightness, compared against the known intrinsic luminosity of such events, calibrated against thousands of supernovae observed at closer distances, where the geometry is simpler, gives a distance. The distance is compared against the recession velocity, and from that comparison, the shape of the universe's expansion history is refined by one more data point. The measurement is quiet. It happens in the middle of the night, in a control room or an office, by someone looking at numbers on a screen. There is no drama in the instant of it, no sensation of discovering something vast, just the careful act of reading what the data says and writing it down. The vastness is in what the numbers mean when they are gathered together and compared against the predictions of cosmological models and found to disagree in a particular direction. The astronomer who sees the residual in a single supernova sees only a number. The astronomer who sees it in 100 supernova consistently in the same direction, that is the moment the picture changes. And the picture that changed because of white dwarfs exploding at a fixed mass calculated by a 19-year-old on an ocean crossing in 1930 is the picture of what the universe is. Not what it contains, not what kinds of stars and galaxies fill it, but what it is made of and what it is doing. The discovery that roughly 70% of the universe's energy content exists as something whose nature is unknown, pressing space apart from the inside, pure consequence that traveled from a quantum mechanical rule through stellar physics, through thermonuclear detonation, through 500 million light-years of intergalactic space to arrive in the data of an astronomical survey. The chain is long, every link in it held. There is a kind of patience in the thought of that chain. Nothing in it was hurried. The progenitor star burned for billions of years without any acceleration of its schedule. The white dwarf cooled at exactly the rate its physics allowed. The accretion from the companion proceeded at the rate that orbital dynamics and stellar evolution permitted. The explosion, when it came, happened at the speed of a detonating nuclear reaction. The light traveled at the speed of light, and the measurement was made when the instruments were ready and the survey was complete. Nothing rushed forward, nothing waited to be dramatic. Each step happened in its own time, in the order the physics required, and the result followed. The Chandrasekhar limit is not a catastrophic thing. It is a boundary written into the quantum structure of matter, derived from first principles, the same wherever in the universe you go, the same for any white dwarf made of any material in any galaxy at any point in cosmic history. It is one of the cleanest examples in all of astrophysics of a physical threshold with universal applicability, a number that nature enforces without exception, a line that every white dwarf either remains below or crosses only once. Below the limit, the cooling continues. The interior crystallizes. The white dwarf dims over billions of years, radiating away the last of its stored heat in a long, slow, continuous dimming that will eventually, across timescales measured in trillions of years, bring it to something close to the temperature of the surrounding space. It will still be there, still held together by electron degeneracy pressure, still carrying the ordered crystalline memory of its former life as a star. Nothing will happen to it. It will simply grow colder and darker and quieter until the distinction between the white dwarf and the space around it becomes a matter of temperature alone. Above the limit, none of that happens. Above the limit, there is a second of fire, and then the scattering of elements into the interstellar medium, and then nothing where a star had been. The limit is approximately 1 4/10 solar masses. It was calculated on a ship. The ship arrived in Southampton. The young man stepped off with his equations, and the limit has been checked and confirmed, and used and built upon ever since, by observations of white dwarfs and binary systems, by the spectral signatures of Type 1a supernovae, by the distances encoded in the brightness of explosions in galaxies so far away that the light from them left before the Earth existed. The number is right. The chain holds. Outside the porthole of that ship, in 1930, the Indian Ocean moved in long, dark swells, carrying the vessel forward across water that had been deep and cold and indifferent long before any mathematics existed to describe the stars. The pencil moved across the paper, the equations balanced. Somewhere far above, in the light that made the sky bright enough to see by day and dark enough to see the stars by night, white dwarfs were accreting and cooling and pressing electrons toward the relativistic limit, following physics that was already fully specified before anyone had written it down. The stars did not know the calculation was being made. The calculation described what the stars were already doing. The light from a Type 1a supernova, setting out from a galaxy 500 million light-years away in the same year that pencil moved across paper, is still traveling. It has not arrived yet. When it does arrive at whatever instrument waits for it, it will carry in its stretched wavelengths and measured brightness another small refinement of the picture. How fast the universe is expanding, how much dark energy it contains, how the geometry of space-time is evolving on the largest scales. All of that still in transit. The light does not hurry. It travels at the only speed available to it, through a space that is quietly, continuously, and without announcement growing larger. And somewhere in the dark between the galaxy where the explosion occurred and the instruments that will eventually catch it, the photons travel on, patient, informative, arriving in their own time, carrying their small piece of the whole enormous picture. A white dwarf newly stripped of its surrounding shell blazes in the far ultraviolet, at temperatures above 100,000 Kelvin. No eye could hold that light. No instrument on Earth's surface could receive it through the atmosphere's filtering layers. The radiation pours outward in wavelengths shorter than violet, shorter than anything the human visual system evolved to detect, crossing the void in all directions from an object smaller than the Earth, radiant and unwitnessed, and entirely silent in the way that all space is silent, the energy real, the sound absent, the cooling already underway. The cooling begins the moment the last nuclear reaction fails. There is no switch, no threshold crossed in an instant. The deepest interior of the star, where temperatures once climbed high enough to fuse helium into carbon, simply grows quieter, the reaction slowing and then ceasing as the fuel runs thin. What remains is heat accumulated over billions of years of stellar burning, stored in the motion of carbon and oxygen ions, trembling in their dense and slowly organizing interior. That heat has nowhere to go except outward, and so it travels, ion by ion, vibration by vibration, toward the surface, where it radiates away as light. The process is patient beyond anything a human sense of patience can quite reach. It will take longer than the current age of the universe for even a modest white dwarf to cool most of the way through. A white dwarf loses its heat through a single channel. It cannot convect the way stars do, churning hot material upward through huge rolling columns of gas. Its surface gravity, roughly 100,000 times stronger than Earth's, holds the thin atmospheric layers in rigid separation, hydrogen above, helium below, the dense interior below that, each layer frozen in place by the immensity of the gravitational field. Instead, heat filters upward through the outer layers, the way light filters through thick glass. Slowly, the opacity of the material governing how fast the deep thermal reservoir can communicate with the radiating surface. The star glows because it still holds warmth from a life that ended long ago, the way a stone pulled from a fire glows red in a dark room, cooling by degrees, surrendering its stored heat to the air around it in silence. In the first tens of millions of years after the white dwarf forms, the cooling is relatively swift, not swift by any ordinary measure, but swift in comparison to what follows. The surface temperature descends from above 100,000 Kelvin through 70,000, through 50,000, through 30. The peak of the radiation shifts from the far ultraviolet toward the near ultraviolet, then into the range of blue-white visible light. A young white dwarf at 25,000 Kelvin glows with a hard blue-white brilliance. Were it placed where the sun now sits, the light reaching the Earth would be intense and blue and wrong, the kind of light that carries too much energy at the short end of the spectrum and too little of the warmth that living things learn to depend on over the long, shallow ages of evolution. Across the next billion years, the cooling continues at its slower pace. The peak emission shifts from blue-white, toward yellow, toward the orange that ancient red stars carry in their outer layers. A white dwarf that once blazed at 25,000 Kelvin passes through 10,000 as the galaxy ages around it. Stars form, others die. Planetary systems build themselves from molecular clouds and then settle into their long orbital routines. and the white dwarf radiates steadily onward, dimming by degrees so small that no observation spanning a human civilization could detect the change directly. Time here is measured not in years, but in billions of years, not in the lifespans of individuals or even species, but in the lifespans of entire geological epochs, repeated many times over. The star that left the white dwarf behind may have been born in a time before the solar system existed. Its hydrogen-burning life lasted 10 billion years. Its red giant phase expanded and subsided over hundreds of millions more. The planetary nebula it shed glowed for tens of thousands of years before thinning into the interstellar medium. All of that is past. What persists now is the remnant, cooling, dimming, carrying in its ion-by-ion vibration the thermal memory of a life that ran its course when the universe was young. At some point in this long descent, something changes. The cooling does not pause in any way the eye could see. From the outside, the white dwarf simply continues to dim and redden, but inside, at the center, where the carbon and oxygen ions are packed to densities far beyond anything found in ordinary matter, the temperature finally drops low enough that the ions begin to organize. They had been moving in a kind of dense, disordered arrangement, not a gas, not a liquid in any ordinary sense, but something in between, a compressed fluid of ions surrounded by a sea of electrons. As the temperature falls toward 10 million Kelvin in the deep interior, the ions begin to settle into a crystalline lattice. Carbon and oxygen arrayed in an ordered geometric structure, the first faint geometry of the future that the cooling star is slowly building for itself. The crystallization releases heat. This is not a paradox, but a consequence of the physics of ordering. When ions shift from disordered motion into the lower energy arrangement of a crystal lattice, the energy difference between the two states does not vanish. It flows outward as thermal energy, adding itself to the heat the white dwarf is already losing through its surface. The result is that the cooling slows, not visibly, not dramatically, but measurably. A pause in the descent from brightness to darkness that lasts not centuries, but hundreds of millions of years, possibly as long as 1 billion years or more in some cases. The white dwarf settles onto a kind of plateau in the record of stellar brightness and temperature, spending longer there than the models without crystallization would predict. This slowing was proposed in theoretical form in the 1960s by Melvin Ruderman and Edwin Salpeter, working through the thermodynamics of dense stellar interiors before any observatory had the tools to confirm it. They calculated that the cooling of old white dwarfs should carry within it the signature of crystallization, a population of stars holding at particular temperatures longer than expected, bunched together in a way that a survey of thousands of white dwarfs might eventually detect. It was a prediction made before the technology existed to test it, filed away in the literature, and carried forward by later generations of researchers who built increasingly sensitive surveys of stellar populations. The confirmation came in 2019. The Gaia Space Telescope, cataloging billions of stars across the Milky Way with a precision of position and brightness that no previous instrument had approached, released a dataset containing the measured temperatures and luminosities of hundreds of thousands of white dwarfs. When astronomers plotted these objects on a diagram of temperature against brightness, a clustering appeared, an excess of white dwarfs sitting at a particular region of the cooling sequence, spending more time there than the smooth cooling models predicted. This region came to be called the Q branch. The pileup was exactly where the models with crystallization said it should be. The latent heat of solidification, the energy released as billions of ions settled into geometric order, deep inside cooling stellar remnants, had written itself into the statistical distribution of 100,000 dead stars across the galaxy. It is a slow kind of evidence. No individual white dwarf reveals it. The crystallization front advances through any single white dwarf over billions of years, spreading outward from the center in a wave of ordering so gradual that no instrument trained on one object for any reasonable span of time could detect the progress directly. The evidence lives only in the accumulation of many objects photographed at a single moment in cosmic time, their distribution across the diagram of temperature and brightness encoding what physics predicts should happen when ancient dense matter slowly organizes itself into geometric stillness. Somewhere in the Milky Way right now, the coolest white dwarfs are radiating at temperatures that human skin could register as warmth, only very close to the surface. Temperatures measured not in tens of thousands of Kelvin, but in thousands. A white dwarf at 5,000 Kelvin glows with a reddish-orange light, dim by the standards of active stars, but still carrying real thermal emission across millions of years. The oldest white dwarfs in the galaxy formed in its earliest epochs, when the first generation of stars burned through their fuel quickly and left their remnants behind in the thick ancient halo around the galactic disk. Some of those remnants have been cooling for 10 or 12 billion years. They glow now at the very faint edge of what telescopes can reliably detect. Instruments built to see in the infrared, the Spitzer Space Telescope, the Wide Field Infrared Survey Explorer, and more recently the James Webb Space Telescope, have found white dwarfs at surface temperatures as low as roughly 3,500 to 4,000 Kelvin, hovering at the boundary between the last faint glow of thermal emission and the darkness that lies beyond. At these temperatures, the spectrum no longer follows the smooth curve of an ideal hot surface. Hydrogen and helium in the thin atmosphere begin to interact in pairs and clusters, their collision-induced absorption distorting the light into shapes that deviate significantly from what a simple thermal emitter would produce. The light comes through sculpted, shaped by atomic and molecular processes that are not present at higher temperatures. The spectrum of these old cold dwarfs, carrying within it the chemistry of the very thin atmospheric layers that gravity has pinned above the dense interior. A white dwarf at 4,000 Kelvin is barely glowing in any light a human eye could perceive in a dark room. It sits at the warm edge of what the human eye registers as visible, far redder and far fainter than anything that looks like a star in the night sky. It would appear, if it appeared at all, as the faintest reddish point, the kind of dim object that only reveals itself through sustained exposure in a long photograph. The universe around it has aged enormously since this object first formed. Stars born in the same stellar generation have long since left the main sequence, swollen into giants, shed their envelopes, and left their own white dwarf remnants behind, younger and hotter. The older remnant drifts through the galactic disk, cooling, dimming, carrying within it the thermal imprint of a stellar life that preceded the formation of the sun. The sun itself will one day become a white dwarf, not for another 5 billion years, a span of time so large that it exceeds the current age of the solar system. When it does, what remains will begin this same cooling descent, starting above 100,000 Kelvin in the ultraviolet, spending billions of years moving through the visible spectrum, eventually reaching the cool, reddish temperatures of the oldest objects currently known. By the time the sun's remnant reaches 4,000 Kelvin, the universe will be roughly 4 times its present age. By the time it cools further still, to 1,000 Kelvin, to a few hundred, to the ambient temperature of interstellar space, the universe will have grown so old that most of what we call active astronomy will no longer be occurring. The era of star formation will be winding down. The bright churning life of galaxies will have passed into the long, quieter phase that cosmologists call the degenerate era, an epoch in which white dwarfs, neutron stars, and brown dwarfs are among the most common remaining objects, with new stars forming only rarely from the dwindling supply of cool gas. In that era, the Milky Way's white dwarfs will number in the hundreds of billions, the accumulated remnants of every sun-like star that ever lived in this galaxy. They will not be arranged as they are now, a population spanning a range of temperatures and ages. They will be converging on the lower end of the temperature scale, the oldest among them already cold and dim beyond all current detection, the younger ones still faintly radiating in the infrared. The galaxy will glow, if glow is the right word, not with the blue light of massive young stars or the yellow warmth of main sequence stars like the sun, but with the faint distributed warmth of uncountable cooling remnants, each one a compressed solar mass of carbon and oxygen, giving up the last of its stored heat to a universe growing gradually colder around it. The end point of all this cooling carries a name, the black dwarf. No such object is believed to exist anywhere in the observable universe today. The time required to cool a white dwarf from its initial blazing temperatures all the way to the ambient temperature of the surrounding space, to reach a state of thermal equilibrium with the universe itself, is estimated at roughly 10 to the power of 100 years. Written out, that number would fill many pages. Compared to the current age of the universe, 13.8 billion years, the time scale for black dwarf formation is so much larger that the comparison is difficult to hold in any intuitive way. The current age of the universe is to the black dwarf timescale, as a single second is to something far beyond what any unit of ordinary time can convey. There is a way to approach this scale without forcing it into a frame it cannot occupy. The universe has existed for roughly 14 billion years. The oldest white dwarfs in the Milky Way have been cooling for 12 billion of those years. They have traveled in that time through most of the visible color range, from ultraviolet to reddish orange, and they are still radiating, still holding warmth, still losing heat through their surfaces, degree by degree, photon by photon, in the patient arithmetic of cooling that began the moment their nuclear fires went out, and they are still nowhere near the end of the process. The cooling that has occurred so far, vast as it is in human terms, is only the first imperceptible fraction of what remains. The black dwarf, if one could be found and examined, would be an object unlike anything that has ever been observed. Dark, cold, not reflecting light, not emitting it, not absorbing it, except in the minimal way that any matter does. Crystalline throughout its carbon and oxygen ions, arranged in the geometric lattice that began forming at the center billions of years earlier and spread outward over unimaginable spans of time until the last layer of the outer crystal met the thin remnant of the atmospheric shell and ordered itself into stillness. A sphere roughly the size of the Earth, containing roughly a solar mass of matter, entirely crystallized, cooled to within a fraction of a degree of absolute zero. It would drift through whatever the galaxy has become in that remote epoch, perhaps a dispersed cloud of dim objects, the stars long since separated from one another by the continuing expansion of space, without generating anything detectable. Inside, something is still happening, though only barely. Electrons still occupy their quantum states, still refused by the laws of quantum mechanics to share those states with one another. The degeneracy pressure that has supported the object since it first formed as a white dwarf, billions or trillions of years earlier, continues without change. It does not depend on temperature. It does not weaken as the object cools. The electrons that first moved into those states when the progenitor star died will still be moving in them faster than the thermal motion, ordered by quantum law rather than heat, when the object has cooled to a temperature no thermometer ever built has needed to measure. The crystallized interior holds another kind of memory. The carbon and oxygen nuclei in their lattice contain in their arrangement a record of the cooling history, the sequence in which the crystallization front advanced, the way impurities and trace elements affected the lattice geometry at different layers, the subtle variations in composition between the layers synthesized at different depths during the original star's helium-burning phase. In principle, if the physics of crystalline dense matter were well enough understood, the interior of a black dwarf would be readable, the way the interior of a slow-formed crystal on Earth can sometimes be read for the conditions under which it grew, a geological record of an entire stellar life compressed into a sphere of ordered ions in the cold dark of a very old universe. None of this is directly observable at present. No black dwarf exists. No instrument can detect an object that emits nothing. The black dwarf is, for now, a theoretical entity, a prediction of physics that will not be confirmed on any timescale that matters to observation. But the prediction is not speculative in the way that some theoretical objects are. It follows from well-confirmed physics, extended across a timescale so large that it exceeds the reach of any possible verification, but carries nonetheless the quiet authority of a calculation that closes correctly. The white dwarfs that do exist, right now, at this moment, blazing in the far ultraviolet, glowing blue-white, radiating yellow or orange, or the dim reddish warmth of the oldest known, are all on the same path. Every one of them is traveling from the bright hot end toward the dark cold end of the cooling sequence, at a pace set by the opacity of its thin outer layers and the thermal capacity of its dense interior. The journey takes so long that the word journey can barely carry the meaning. It is more like a property than a movement, the way a mountain is slowly being eroded, not traveling toward flatness, but simply having flatness as its eventual geological fate, the erosion already in progress, the mountain still a mountain, the process real and steady and patient beyond any need for witness. In the oldest surviving clusters of stars in the Milky Way, globular clusters, dense spherical gatherings of hundreds of thousands of stars that formed when the galaxy itself was young, the white dwarfs carry extraordinary information in their temperatures. The coolest white dwarfs in a cluster are the oldest, having had the longest time to cool. By mapping the distribution of white dwarf temperatures within a cluster and comparing that distribution to theoretical cooling curves, astronomers can read the age of the cluster itself from the faint end of the cooling sequence, the point below which no white dwarfs appear, because the cluster has not existed long enough for any white dwarf to cool that far. In the globular cluster M4, one of the nearest clusters to the solar system, at a distance of roughly 7,200 light-years, a long campaign with the Hubble Space Telescope resolved individual white dwarfs far below the detection limit of ground-based instruments. The faintest objects in the image, barely distinguishable from the noise of the detector, were white dwarfs that had been cooling for nearly the entire age of the universe. The analysis of their temperatures suggested that the cluster itself formed roughly 12.5 billion years ago, old enough to have been present when the universe was only a small fraction of its current age, old enough that its first stars would have formed from gas that had processed only a small fraction of the heavy elements that now fill the periodic table. That faint cluster image holds something worth dwelling on. In a single long exposure taken by a telescope orbiting above the atmosphere, the accumulated light of tiny, cooling, ancient stellar remnants, objects that generate no new energy, that exist purely as the slow-release thermal reservoirs of dead stars, was gathered and recorded. The light from those objects set out on its journey to the Hubble mirror from a distance of 7,200 light-years, crossing space that the solar system has not yet visited and will not visit in any conceivable future. The white dwarfs that emitted it were already old when they emitted it, already billions of years into their cooling descent, already far redder and dimmer than the objects they had been when they first formed. The cooling sequence in M4 reaches into a time before the solar system existed at all. The stars that became those white dwarfs lived and died before the sun's parent molecular cloud had gathered into anything resembling a star. The carbon and oxygen in those cluster white dwarfs compressed into crystallizing interiors, cooling by degrees across the billions of years, was made in stellar cores that burned out before the Earth's first ocean formed. The universe was already doing this, already generating stellar remnants and setting them on this patient cooling path, long before the particular constellation of circumstances that produced the solar system arranged themselves in this corner of the galaxy. Across the galaxy as a whole, surveys counting and cataloging white dwarfs have revealed the shape of what is called the white dwarf luminosity function, a tally of how many white dwarfs exist at each level of brightness, stretching from the hot young objects near the top of the cooling sequence to the faintest, coldest objects still detectable near the bottom. The shape of this distribution carries real information. Hotter, more recently formed white dwarfs are numerous because the galaxy has been forming stars steadily for billions of years, and many of those stars have recently finished their evolution. Cooler, older white dwarfs become less numerous at the faint end, not because they don't exist, but because time and the pace of cooling set a lower limit. The faintest white dwarfs detectable represent the cooling progress made since the galaxy first began forming stars. Beyond a certain faintness, there are no white dwarfs, not because they were never born, but because they have not yet had time to cool that far. The sharp drop at the faint end of the luminosity function is, in this sense, a record of the galaxy's age written in the temperatures of its cooling dead stars. It was from the shape of this distribution and the precise location of that cutoff that astronomers in the late 20th century were able to derive independent estimates of how long the Milky Way's disk has been forming stars, ages in the range of 8 to 10 billion years, consistent with but independent from other methods that use main sequence turnoff ages in old clusters. The white dwarfs confirmed what the other methods suggested, each line of evidence arriving at the same number from a different direction, the convergence quiet and thorough and satisfying in the way that all independent confirmation is satisfying. The cooling of a white dwarf is slow enough that it seems from outside to be a kind of stillness, but it is not stillness. Deep inside, in the crystallizing core, the lattice is advancing outward through the dense interior, the crystallization front spreading through ion after ion in an ordering process that releases a small quantity of heat with every step. Closer to the surface, where the matter is less compressed, the material remains in a dense, disordered state, hot enough that the ions have not yet begun to organize into a lattice. Above that, the thin atmospheric layers, hydrogen floating above helium by the overwhelming action of gravity, filter the outward flow of heat, slowing it, shaping it into the specific wavelengths of a thermal spectrum at whatever temperature the surface has reached. Every layer of the white dwarf interior is involved in this slow, ordered process. The core crystallizes first, then the surrounding material, layer by layer, as the temperature falls inward from the surface over billions of years. The outer layers remain disordered longer, held above the crystallization threshold by the heat still flowing through them from below. Eventually, in timescales measured in tens of billions of years, even the outer material cools enough to order itself. The crystallization front reaches the edge of the dense interior, and the object is, at that point, crystallized through from center to the base of the thin atmospheric shell. The ions sit in their lattice positions, trembling with a tiny residual thermal energy that will itself take billions more years to fully radiate away. The James Webb Space Telescope, launched in late 2021 and operating at a stable position far from the Earth's warmth, has begun resolving white dwarfs at the cool end of the temperature scale with a sensitivity that previous infrared telescopes could not match. Its mirror cooled passively to temperatures low enough that its own thermal emission does not overwhelm the faint infrared signals it is trying to detect, can resolve the spectra of white dwarfs in the range of 3,000 to 5,000 Kelvin objects, so cool and dim that they sit at the very edge of what even this instrument can study cleanly. In those spectra, the deviations from a smooth thermal curve reveal the chemistry of the thin atmospheric layers, hydrogen and helium in their collision-induced absorption states. Trace amounts of heavier elements, where planetary debris has recently been accreted and settled into the photosphere. The detailed shape of the infrared spectrum carries within it the physics of the atmospheric chemistry at those cool temperatures, and from that chemistry, further constraints on the white dwarf's cooling age and composition. The work of watching white dwarfs cool is in practice a very long project. The cooling time of even the youngest white dwarfs vastly exceeds any human observation program. What is possible instead is the statistical study of populations, comparing the distributions of white dwarf temperatures and luminosities against models that predict what those distributions should look like given a particular star formation history and a particular set of cooling physics. Each new survey adds more objects. Each more precise set of measurements tightens the constraints on the models. The Q-branch clustering, the shape of the luminosity function, the ages derived for ancient clusters. These are all pieces of a coherent picture in which the cooling of stellar remnants over billions of years is legible in the light of the present sky. A single white dwarf holds within it the compressed thermal history of a star. The star itself may have lived for 8 or 10 billion years on the main sequence, fusing hydrogen in its core, balanced between the outward push of radiation and the inward pull of gravity. The helium it accumulated over those billions of years eventually fused in turn, building the carbon and oxygen that now form the dense interior. All of that energy, all of that nuclear burning, all of that light that warmed whatever worlds may have orbited the progenitor star, it is gone. What remains is only the heat that was left behind when the burning stopped, slowly draining away through the surface into the surrounding dark. At the moment that a cooling white dwarf reaches thermal equilibrium with the universe around it, the moment when the temperature of the object equals the temperature of the diffuse radiation that fills all of space, the last photon that could be properly called emission from the white dwarf itself would leave the surface. After that, the object would absorb exactly as much energy from the cosmic background as it radiated. It would be, in every physical sense, finished, not destroyed, not collapsed, not gone, still there, still containing a solar mass of carbon and oxygen in a crystalline lattice, still held against gravity by electron degeneracy pressure, still occupying an Earth-sized sphere of dense organized matter drifting through whatever the universe has become by then. Simply cold, simply dark, simply still. The universe right now holds no such objects. Every white dwarf that has ever formed is still warmer than the ambient temperature of space, still losing heat through its surface, still somewhere on the long cooling path between its blazing beginning and its theoretical cold end. The oldest white dwarfs in the Milky Way are among the coldest things in the universe, colder than most stars by a vast margin, cooler than any active stellar surface, and they are still radiating. The thermal energy that was left inside them when their nuclear lives ended 10 or 12 billion years ago has not yet fully departed. A small fraction of it remains, spreading slowly outward through the dense matter, crossing the thin atmospheric layers, escaping as the dimmest and reddest light these objects now produce. Something drifts in the oldest parts of the galaxy, very faint, radiating at a temperature not far above the coolest known objects of any stellar kind. It holds within it carbon that was assembled in the core of a star before the sun was born. Its crystallizing interior has been advancing, ion by ion, through its center for billions of years. The light it emits right now, right at this moment, will cross 70 or 100 or 500 light years and arrive at no instrument, observed by nothing, simply crossing the interstellar space that surrounds these oldest remnants in the quiet reaches of the galactic halo. The universe does not require the light to be received. The cooling does not require a witness. It continues with the same steady patience it has carried since the beginning of the process, the same patient release of stored warmth into a surrounding dark that is itself, slowly and over unimaginable timescales, cooling toward a stillness that nothing now alive will ever see. Every white dwarf visible in the present sky is still bright enough to be found. Every one of them is still giving something back: light, warmth, information about its cooling history and its chemical composition, and the planetary debris that has fallen into it from the remains of whatever worlds once orbited the star it came from. The process is not finished. It is simply very slow. The universe that contains these objects is itself still young enough that none of them has reached its end, and the light they still emit, however dim, however shifted toward the infrared and away from anything a human eye could easily detect, is real and continuous and present, the last long breath of a stellar life, extended across time so deep that the breath itself is a kind of eternity. Among all the surveys ever made of the night sky, one of the strangest pictures came not from a single image, but from a count. Astronomers gathered the measured brightnesses of tens of thousands of cooling stellar remnants and arranged them in order, from the hottest and brightest down through the dim and the dimmer, until the list simply stopped. Not because the survey ended, not because the instruments lost their reach. The list stopped because the objects stopped. Below a certain faintness, in the direction of the oldest stars in the Milky Way's disk, there were no more white dwarfs to be found. And in that absence, in that clean, sharp edge where the census fell to nothing, was written something no clock had ever recorded. The white dwarf luminosity function is what astronomers call this distribution. It is less an image than a shape made from counting. Survey a wide enough region of sky, measure each white dwarf's brightness carefully, and the function tells how many exist at each level of luminosity. It rises and falls. It holds a steady plateau across the middle range. And then toward the faint end, it drops, not gradually, not in a long trailing tail, but in something close to a cliff. The drop is real. It marks the point below which no white dwarf in the Milky Way's disk has yet had time to cool. It is the thermal frontier of the galaxy's own age. James Liebert and his colleagues mapped this boundary in 1987, working through ground-based data collected across years of patient observation, and what they held in their hands when the count was done was an independent age for the galactic disk, something between 8 and 10 billion years, derived not from radioactive decay or stellar evolution models alone, but from the simple, irreversible fact that heat takes time to leave a body, and these particular bodies had only had so much time. The logic is plain and carries its own weight slowly. A white dwarf forms at temperatures above 100,000 Kelvin and cools from that point forward, spending all the heat stored in its interior through the only channel available to it, light radiated from its surface, photon by slow photon, across billions of years. If a population of white dwarfs formed together, they would cool together, fanning out across the luminosity function, like runners spreading along a track. The oldest and coolest would cluster at the faint end. None would appear below the faint end cutoff, because none would have had time to reach it. The cutoff, then, is a boundary drawn not by observation limits, but by time itself. The Milky Way's disk is old enough to produce white dwarfs of a certain minimum brightness, and no older. Every white dwarf below that line has not yet formed. It is still somewhere higher on the curve, still a degree or two warmer than the threshold, still radiating its last reserves of ancient heat. The Sloan Digital Sky Survey extended this count dramatically. So did the ESA Gaia mission, which swept the sky with a precision that gathered stellar positions and motions and luminosities for more than 1 billion objects, white dwarfs among them. With those surveys, the faint end cutoff sharpened. The estimate for the thin disk settled between 8 and 10 billion years, older than the solar system, younger than the galaxy's ancient halo, a number that arrived not from any single star's chemistry, but from the collective silence of all the white dwarfs that had not yet grown cool enough to fall below the edge. A handful of these old white dwarfs, some of the coolest and faintest found anywhere in the sky, do not sit in the disk of the galaxy at all. They belong to something far older, the globular clusters, dense spherical swarms of hundreds of thousands of stars that formed in the galaxy's earliest era, when the universe was young enough that most of the matter it contained had barely begun to settle into the structures now visible across the night. The globular cluster known as Messier 4 sits roughly 7,200 light-years away in the direction of the constellation Scorpius. From Earth it appears as a soft smear of light, barely resolved to the naked eye, resolving through a telescope into a city of stars so tightly packed that their mutual gravity has held them in orbit around one another for longer than the solar system has existed. In 2004, Harvey Richer and his collaborators turned the Hubble Space Telescope toward the faint heart of that cluster and waited not for an event, but for exposure time to accumulate, photon by patient photon, until the dimmest points of light in the cluster began to emerge from the background noise. What they found at the bottom of the cluster's white dwarf cooling sequence were points of light so faint that without Hubble's mirror, they would have been invisible. These were white dwarfs that had been cooling since the cluster's stars first died, which is to say, since stars far more massive than the Sun burned through their fuel in the first billion years of cosmic history. The cluster's age, read from the faint end cutoff of its white dwarf sequence and compared against theoretical cooling curves, came to roughly 12.5 billion years, not far from the age of the universe itself, arrived at from a completely independent direction. The main sequence turnoff method, which reads stellar age from the color and brightness of the hottest stars still fusing hydrogen in a cluster, had given similar numbers. The white dwarf cooling method confirmed them using entirely different physics, measured in entirely different light. Two clocks set at the same moment, by two different mechanisms, running for more than 12 billion years, and when read, agreeing. The agreement between methods is itself a kind of stillness. It means the picture is not wrong. It means the universe's age and the age of its oldest visible structures are consistent with one another, that the physics of how stars cool and the physics of how stars evolve on the main sequence are mutually coherent across 12 billion years of continuous running. In science, that kind of agreement carries weight, and it settles quietly into the evidence without fanfare, a deep harmony that does not announce itself, but simply holds. What the Gaia mission added to all of this was finer resolution across the full population. With hundreds of thousands of white dwarfs cataloged and their positions on the Hertzsprung-Russell diagram plotted, temperature on one axis, luminosity on the other, patterns emerged that no smaller survey could have shown. Among the most striking was a feature now called the Q branch, a clustering of white dwarfs along a band in the diagram, where theory said they should have moved through quickly, but observation found them lingering. More white dwarfs existed there than cooling models predicted. The excess was not large enough to be obvious in a small sample, but unmistakable once Gaia had counted enough of them to make the statistical pattern clear. The explanation drew on physics predicted decades earlier. As a white dwarf's interior cools, the carbon and oxygen ions in its deep core eventually lose enough thermal energy to arrange themselves into a crystalline lattice, not a sudden snap, but a slow propagation, spreading from the center outward over hundreds of millions of years. When ions crystallize, they release latent heat, the same way water releases a small pulse of warmth when it freezes into ice. In a white dwarf, that released energy seeps outward through the interior and buoys the star's brightness for far longer than it would otherwise hold. The Q branch in Gaia's data was a population of white dwarfs that had slowed their cooling, pausing for somewhere between 1 and 2 billion years longer than expected, because crystallization was feeding additional heat back into the system. Malvin Ruderman and Edwin Salpeter had proposed the physics behind this process in the 1960s, working from theory alone with no way to confirm it. The confirmation waited for a space telescope capable of counting hundreds of thousands of white dwarfs at once and resolving the subtle shape of their distribution in luminosity and temperature. The prediction and the observation finally met each other in 2019 across 6 decades. The crystallizing interior of a white dwarf is not dramatic. It does not flash or crack. It advances in silence through the compressed interior, ion settling beside ion, the lattice propagating outward, one thin shell at a time, the ordered structure spreading slowly through the body of the star, the way a frost advances across still water on a night that has grown very cold. The latent heat it releases is small by stellar standards, a modest supplementary warmth, but the interior of a cooling white dwarf is so dense and so thermally sealed that even small sources of heat extend the cooling time by geological intervals. A star that would otherwise spend a certain number of billion years crossing the Q branch of the diagram instead spends a billion or two more years there, its light a little steadier than pure cooling would allow, before the crystallization front reaches the outer layers and the heat supply is finally spent. All of this, the luminosity function, the Q branch, the ancient clusters and their faint cold remnants, describes white dwarfs in terms of what they tell us about time. But there is another kind of reading, one that does not measure age at all, and instead reads chemistry. And it comes from a detail so small, so narrow in the spectrum of stellar light, that it can be missed entirely unless one is looking for it. A thin, dark line in the light of a white dwarf that should not, by all physical reasoning, be there at all. The surface gravity of a white dwarf, roughly 100,000 times stronger than Earth's, has a precise and unforgiving effect on the star's thin atmosphere. Any element heavier than hydrogen sinks. It sinks within days in the hottest white dwarfs, within millions of years in the cooler ones, but in any case it sinks. The hydrogen floats because it is the lightest. The helium settles just below. Everything heavier, carbon, iron, calcium, silicon, magnesium, disappears downward into the opaque interior, lost to observation, within timescales that are short by any astronomical measure. A white dwarf's observable photosphere, absent any external disturbance, should be nearly pure, hydrogen, or in some cases helium, nothing else, which is why the calcium K line at 3,933 angstroms, a narrow dark notch in the near ultraviolet portion of the spectrum, the signature absorption of singly ionized calcium, appears so quietly and so tellingly in the spectra of a significant fraction of white dwarfs. It should not be there. Calcium is heavy. Gravity should have drawn it down and out of view long ago, in a matter of decades at most, for a warm white dwarf, in perhaps 1,000,000 years for a cool one. When it appears in a spectrum, the calcium is fresh. It arrived recently. Something delivered it to the stellar surface, and that something must still be arriving, or must have arrived so recently that the gravitational clock has not yet run it down. The white dwarf has been contaminated. The contaminating material is in most cases solid, rocky, the remnant debris of something that once had structure, a body large enough to have accreted into a coherent form and solid enough to carry a distinct elemental composition, preserved through billions of years of planetary evolution around its parent star. What the gravity of the white dwarf does to that body is gradual and complete. An asteroid or a minor planet passing within a certain distance of the white dwarf, within roughly 1 solar radius of the stellar surface, enters a zone where the tidal difference in gravity between its near side and its far side exceeds the material strength holding it together. The body stretches, it shreds, it dissolves into a disk of debris orbiting the white dwarf in the same plane the original body traced. A slow flat ring of dust and gas spiraling inward under the drag of its own interactions, settling over thousands to millions of years onto the stellar surface below. The Spitzer Space Telescope first detected the infrared excess from these debris disks, the warm glow of dust heated by proximity to the white dwarf, revealing that the disks existed, that they were real and present around a number of white dwarfs, not as a theoretical proposal, but as a measured source of excess heat. The picture became clearer with time and with additional observations until it was possible to say with confidence that a significant fraction, somewhere around 25 to 50% of all white dwarfs, observed carefully enough, show evidence of pollution by external rocky material. The number may be higher. The sensitivity of observations keeps improving. Each additional element of the periodic table identified in a polluted white dwarf's photosphere adds another line of chemical evidence to the record. Because it is not only calcium that arrives, iron arrives, magnesium arrives, silicon, oxygen, nickel, each element with its own absorption feature, and the ultraviolet, its own narrow notch in the spectrum, each readable if the telescope is large enough and the exposure long enough. The Hubble Space Telescope's ultraviolet spectrograph has been the primary instrument for reading these features, working at wavelengths the atmosphere blocks from the ground, resolving the absorption signatures of elements delivered to white dwarf surfaces from the wreckage of their planetary systems. What the spectra show when the elemental ratios are carefully extracted is a chemical profile, the bulk composition of the accreted material, expressed as the relative abundances of its constituent elements, which carry within them the full history of where and how that material formed. Rocky bodies in planetary systems do not have arbitrary compositions. They reflect the chemistry of the disk from which they formed, the temperature at which they condensed, the degree to which they differentiated, whether they grew large enough for their interiors to melt and separate into a metallic core surrounded by a rocky mantle, the way Earth did, or whether they remained more primitive, preserving the well-mixed chemistry of the early solar nebula. The ratio of iron to magnesium tells something about differentiation. The ratio of silicon to oxygen tells something about oxidation state. Water-bearing minerals leave their own trace in the elemental abundances. Each ratio is a question answered by the chemistry, an answer carried across billions of years through the body of the accreted rocky fragment and deposited, finally, into the photosphere of the white dwarf, where it can be read by instruments made by descendants of the very planetary formation it records. Most of the rocky material that has been analyzed in this way resembles what geochemists call CI chondritic meteorites, a class of primitive stony meteorites found on Earth, believed to represent the most unfractionated samples of the early solar nebula available for direct study. The match is not perfect in every case. Some polluted white dwarfs show compositions that suggest the accreted material had already differentiated, already separated into a core-like or mantle-like component, the signature of a body large enough to have melted in its own radiogenic heat. Others show compositions consistent with water-bearing silicates, the kind of rocky material that, in our own solar system, formed in the outer asteroid belt where temperatures were low enough for water ice to condense into solids. The diversity of compositions across different polluted white dwarfs mirrors the diversity of rocky material in planetary systems, which suggests that planetary formation is not a narrow or unusual process, but one that plays out across a wide range of conditions around a wide range of stars, leaving behind, in each case, a planetary system's worth of solid bodies that persist in orbit around the white dwarf remnant for billions of years after the star itself has died. The picture that assembles itself from all of this is of planetary systems as durable things. A sun-like star burns for 10 billion years. In its latter stages, it expands into a red giant and sheds most of its mass, and the shock of that mass loss disrupts the orbits of everything that survived the giant phase. The surviving planets and asteroids and minor bodies are perturbed, their gravitational interactions, running now in the altered potential well left by the mass-losing star, slowly reshape their orbits over millions to hundreds of millions of years. Some are scattered inward, some encounter the white dwarf's tidal disruption zone and are shredded. The debris falls, and the white dwarf spectrum, for a brief interval on the scale of stellar evolution, carries the chemical signature of a planetary body. Brief in stellar terms may still be millions of years, and so surveying a large population of white dwarfs at any given time, a quarter or more show this contamination, because at any given moment, a significant fraction of all white dwarf planetary systems are in the process of delivering rocky debris to their stellar remnant. This is not a violent picture, though disruption is part of it. It is slow, The tidal shredding of an asteroid does not happen in a flash, but over many orbital passes, the body gradually stretching and breaking apart, its debris spreading into a disk over thousands of years. The infall of that disk material onto the white dwarf surface is slower still, governed by subtle forces, gas pressure, Poynting Robertson drag, collisional grinding, that operate on timescales that would span entire human civilizations. The white dwarf below simply waits, its surface integrating the incoming material, its spectrum recording what has arrived, its gravity doing steadily what it does to everything, pulling it down, sorting it by weight, swallowing it into the silence below the photosphere. There is something in the image that asks to be held for a moment, a rocky planet or the remnant of one, an asteroid that was never large enough to be a planet, but carries within it the condensed chemistry of a solar system's early construction, formed in orbit around a star 4 or 5 or 8 billion years ago, in an era when the universe was younger and star formation was common, and planetary systems were assembling themselves across the galaxy in their hundreds of billions. The planet forms, the star burns for billions of years, the planet orbits, patient in its long arc. The star swells into a red giant, perhaps engulfing the inner system, perhaps not. It sheds its outer layers in a long, slow breath. The white dwarf is exposed. The planet's orbit changes in the new gravitational landscape. Millions or hundreds of millions of years pass. The orbit decays or is scattered inward. The body crosses the tidal boundary and dissolves. The debris disk spirals down. The chemistry of the planet's own interior, iron from its core, magnesium from its mantle, silicon from its crust, arrives at the surface of the white dwarf. And in the stellar spectrum, an astronomer reads the elemental ratios and reconstructs from those faint absorption lines the bulk composition of an extrasolar rocky world that no instrument could ever have imaged or visited directly. The calcium K line at 3,933 angstroms is dark and narrow. Against the background of a white dwarf's nearly featureless spectrum, a broad, smooth continuum shaped by the temperature of the surface, the absorption line is a small thing. It is a slight dimming in a specific color of near ultraviolet light, a fraction of the total signal, detectable only because the instrument is calibrated finely and the exposure is long enough. But the information it carries is not small. It carries the story of a world that formed around another star, orbited through billions of years of stellar history, survived the death of its sun, and ended at last in the gravity of the stellar remnant it had orbited. The white dwarf absorbed it, the spectrum preserved it, and from 4,000 light-years away, give or take, a telescope gathered the light, and the signal was read. The initial to final mass relationship maps out the arithmetic of what the death of a star returns to the galaxy. A star of 2 solar masses, twice the mass of the sun, burning its hydrogen much faster, living perhaps for only a couple of billion years, leaves behind a white dwarf of roughly half a solar mass. The numbers are specific, around 0, 55 solar masses for a 2 solar mass progenitor, according to the best current picture drawn from observations of white dwarfs in stellar clusters, where the progenitor masses can be estimated from the cluster's age and the turn-off point of its main sequence. The gap between those two numbers, between roughly 2 solar masses in and 0, 55 solar masses out, is the material return to the interstellar medium during the red giant and asymptotic giant branch phases, when stellar winds and thermal pulses drove the outer layers off into the surrounding space. Roughly 3/4 of the original star's mass went back into the medium. Only 1/4 remains, locked in the white dwarf, slowly cooling. That returned material is not merely hydrogen and helium. In its passage through the stellar interior, it was processed. Carbon was made in the helium-burning core. Nitrogen was synthesized in the hydrogen-burning shell. Heavy elements forged through the slow neutron capture process. Elements heavier than iron, including barium, strontium, cerium, and others, were brought to the stellar surface through the convective dredge-up events of the asymptotic giant branch phase and cast into space when the stellar winds stripped the outer layers away. The planetary nebula that briefly glowed around the forming white dwarf was not simply old stellar material being expelled. It was enriched material, chemically altered by the full sequence of nuclear burning the star had performed across its lifetime. The interstellar medium into which it expanded was made fractionally richer in heavy elements by that contribution, and the stars that form next in that region of the galaxy will condense from a cloud slightly more chemically complex than the one from which their predecessors formed. In this way, the stellar life cycle is also a chemical cycle, and the white dwarf at its center, quiet, dense, cooling, is the part that does not go back. It is the remainder, the fraction too tightly bound to return, held in place by the quantum pressure of its compressed electrons against the pull of its own gravity for longer than any geological timescale can convey. The oldest white dwarfs in the Milky Way formed from stars that themselves formed more than 10 billion years ago. Those white dwarfs have been cooling ever since. The light they emit now is faint and shifted toward the red. Their surface temperatures fallen to a few thousand Kelvin, their spectra distorted by the collision-induced absorption of hydrogen and helium molecules in their dense, cool atmospheres. The James Webb Space Telescope has begun to resolve objects like these in detail. White dwarfs, so cool and so faint that they sit at the edge of what even the most sensitive instruments can detect, their spectral shapes departing significantly from a smooth thermal curve because the molecular processes in their atmospheres are complex enough to sculpt the light before it escapes. These objects are the oldest stellar remnants in the galaxy that can still be directly observed. They have not cooled completely. They are still, after 10 billion years, fractionally warmer than the space around them, still releasing the last deep reserves of heat stored in their crystalline interiors, still shining, barely faintly, in the deep infrared. The coolest of them glow at temperatures around 3,500 to 4,000 Kelvin. That is warm enough to glow a deep dim red, not visible to the naked eye at their distances, but measurable through sensitive infrared detectors. At those temperatures, the surface of a white dwarf is cool enough that some of the processes more familiar from the surfaces of cool red dwarf stars begin to appear. The spectra grow complicated. The smooth black body continuum is replaced by something shaped and notched and asymmetric, the product of molecular absorption carving channels through the emitted light. Understanding those spectra requires models of cool, dense, high-gravity atmospheres that are still being developed, still being refined, as new observations from more powerful telescopes push the detectable boundary to fainter and fainter objects. No white dwarf in the history of the universe has yet had time to cool completely. The theoretical endpoint, the black dwarf, cold and crystalline and entirely dark, carrying no detectable luminosity, emitting no photons, requires a cooling time so far beyond the current age of the universe that the number becomes almost a different kind of thing than a number. The universe is currently somewhere around 14 billion years old. A white dwarf left to cool in isolation would require something closer to 10, followed by 100 zeros in years, to reach equilibrium with the surrounding space. There are no black dwarfs. There have never been any. Every white dwarf that has ever formed is still somewhere in its cooling sequence, still releasing heat, still a degree or fraction of a degree warmer than the void around it, still contributing its small share of photons to the background luminosity of the galaxy. The youngest are ultraviolet bright, recently exposed from their planetary nebula, radiating fiercely at temperatures above 100,000 Kelvin. The oldest are barely glowing, deep in the infrared, 10 billion years into their long descent. All of them are still descending. None has arrived. There is something in this that settles the mind. The universe is old enough that its earliest white dwarfs have spent 10 billion years cooling, and they have not finished. The process is not broken or arrested. It is simply that slow. Heat leaves these objects through their surfaces at a rate governed by the opacity of their thin atmospheres, and the interior thermal reservoir is enormous by the standard of any radiating surface. The star that formed the white dwarf spent billions of years building up that thermal reserve, and the white dwarf has spent billions of years giving it back, and it still has billions of years of giving ahead of it. The cooling is not hurried. Nothing about a white dwarf is hurried. It does not fuse. It does not convect in any significant way through most of its interior. It simply sits, dense and quiet, and releases heat steadily, measurably, photon by photon, into the surrounding dark. The planetary remnants orbiting around these objects orbit in that same quiet. An asteroid that has survived the death of its star, the violent dispersal of the red giant phase, the shock of mass loss, and the reshaping of every orbital resonance in the system. An asteroid that made it through all of that and now circles the white dwarf in a slow ellipse, millions of kilometers out, in a planetary system transformed beyond recognition from what it was when the star was young. That asteroid knows nothing of the history it carries. It is inert. It orbits. It carries in its bulk chemistry a record of its formation, the temperature at which it condensed, the elements available when it grew, whether it differentiated or stayed primitive. And that record will persist, sealed in solid rock, until something disturbs the orbit enough to bring it inside the tidal radius. Then it will dissolve. Then the record will be read in light. The calcium K absorption line sits at 3,933 angstroms. It is a dark notch in the spectrum of a cooling stellar remnant, barely a feature, the kind of thing that in early spectroscopic surveys was sometimes overlooked entirely. It announces, in the only language available to it, the language of light, absorbed at specific energies by specific electronic transitions in specific atoms, that a rocky world was here, and that it ended here, and that its chemistry is preserved in the photosphere of the star that destroyed it. Iron from its core, magnesium from its mantle, silicon from its rocky crust, oxygen threaded through all of them. The ratios of these elements, measured through ultraviolet spectrographs and compared against the compositions of known meteorite classes, reconstruct the geochemical profile of an extrasolar rocky body as precisely as any direct measurement of a solar system sample. The composition of a distant, invisible, long-destroyed rocky world, a world that formed around a star that no longer exists in anything like its original form, is legible in the light of its destroyer. The white dwarfs of the Milky Way carry all of this at once. They are clocks, their cooling rates encoding the ages of stellar populations across the galaxy's full history. They are chemical archives, their polluted atmospheres preserving the geochemistry of destroyed extrasolar rocky bodies. They are the endpoints of the lives of the vast majority of all stars that have ever burned. Everything below, roughly 8 solar masses, ends as a white dwarf, and most stars formed over the history of the universe fall well below that threshold. The galaxy is full of them, hundreds of billions by most estimates, the accumulated stellar remnants of 10 billion years of star formation spread through the disk and the halo and the globular clusters, cooling at their different rates, each one a preserved record of the star that formed it, and the planetary system that orbited it, and the composition of the interstellar cloud from which all of it once condensed. They do not announce themselves. They are not bright. The nearest white dwarf, Sirius B, the smaller companion of the night sky's brightest star, is invisible to the naked eye, despite lying less than 9 light-years away, its faint light overwhelmed in the glare of Sirius A beside it. The others are fainter still. The coolest and oldest are so faint they appear only in the deepest surveys, in images accumulated over hours of telescope time, as points of light barely distinguishable from the noise. They are the quiet part of the sky, and they have been there cooling since long before any instrument was built to detect them. From within the thin slice of a white dwarf's atmosphere, a layer less than 100 kilometers deep, floating above a solid interior that contains nearly a full solar mass of compressed matter, the universe presents itself in a particular way. The surface gravity is immense. The atmosphere is thin to the point of near invisibility. The star below does not burn. It does not convect significantly. It does not rotate rapidly or erupt or pulse. It simply cools, its interior crystallizing ion by ion from the center outward, its surface temperature declining by degrees over millions of years, its spectral peak drifting slowly through the visible range toward the red, and then toward the infrared, and then toward the darkness beyond the reach of current instruments. In the spectrum of a cool white dwarf, in the dim, distorted curve of light that escapes from a surface at 4,000 Kelvin, shaped by molecular absorption and the extreme pressure of the dense atmosphere, is everything that instrument science can currently extract about these ancient objects. Temperatures, surface gravities, atmospheric compositions, cooling ages, chemical contamination from rocky debris, the ages of the stellar populations that produced them. These are not small things. They are answers to questions that matter across the full breadth of what is understood about the history of the universe, and 1/12 day of with how old it is, how stars of different masses evolve and return their material, how common rocky planet formation is, and what the chemistry of that formation looks like from star to star and system to system across the galaxy. A white dwarf is not the absence of a star. It is the concentrated remainder, the part that gravity could not pull further, the part that quantum pressure holds in place, the part that carries within its dense interior the thermal memory of all the nuclear burning that came before and releases that memory slowly across timescales that dwarf anything the biological world can furnish as comparison. The star that made it spent billions of years fusing hydrogen and helium and building its chemical complexity. It shed most of that complexity back into space. What remains is the core, compressed, ordered, cooling, a small warm sphere in the dark, surrounded in many cases by the debris of a planetary system, still in slow orbit, still falling inward, still delivering its chemical record to the stellar surface, and all of it is still happening now. Somewhere in the Milky Way, a planetary nebula is thinning and dispersing, revealing at its center the freshly exposed surface of a new white dwarf blazing in the far ultraviolet. Somewhere, the faint debris disk of a disrupted asteroid is spiraling inward around a cooling white dwarf, and calcium is settling into the stellar atmosphere in concentrations just detectable from Earth. Somewhere in the interior of a white dwarf that formed 6 or 8 billion years ago, The crystallization front is advancing outward through the dense ionic lattice, ion by silent ion, releasing the last of its latent heat into the cooling interior.